Alright, time for another draftphysics.com video presentation and such, so forth and whatnot. Usual routine to start. Alright, so the Michael physics guy has done a video on Doppler shift, so we'll talk a little bit about that first. And then, if he's interested, talk a little bit about what this whole energy problem that exists for 2 years of controversy with people over the word energy conservation, the concept, and what is conserved, momentum or whatever this kinetic energy stuff is, the fable. Anyway, so Doppler shift. I guess I'll play just a little tiny piece of the video. So he's just basically explaining Doppler shift. I mean, he's doing it in the context of astronomy, which will lead to the expanding universe kind of crap eventually, probably.
Light was originally emitted, the rest wavelength, and I know I can measure what is the wavelength of light that I see when we detect this light.
So I got it sped up a little bit. So obviously I would just analogize it more with like a argument about frequency. And we don't need to bother with waves and wavelengths. It's just a period that something happens. So if I'm firing a gun and you move towards me while I'm doing it, the bullets will hit you quicker. If you move away from me, it'll take longer for each bullet to hit you. That's all there is. So that's the Doppler effect. So it doesn't matter whether I move the gun towards you, then the bullets will hit you more frequently. If I move the gun away from you, the bullets will hit you less frequently. Or you move towards the gun. It just means that you're closing the space between a frequency, a period between events. And those events will appear to happen sooner. They will happen sooner. If you're closing the distance between the two objects, if you're expanding the distance, then they'll happen less frequently. Alright, so it's not that complicated, but okay, whatever, make videos on it, it's alright. It's sort of something that, I don't know, should be taught like grammar schoolish.
Right? Then we can go through this calculation and figure out how fast towards us or away from us is this particular object moving.
Right, so he just does that 3 times, and with light frequencies. And nothing much to it, really. You just subtract the 2 numbers, divide by the original number, and multiply by the speed of light, and there you go. So it's not saying much. It's just saying about how fast the distance is being closed or how fast the distance is being expanded, and it doesn't really tell you who's moving which way. You have to deduce that from other facts. Okay. Alright, so that's probably enough of the video, and then I'll just do my counter argument to where the video probably will go in some day. Someday he'll go further and say something. Oh, sorry about that. Yeah, I had the chat box in the way, but minor detail, frankly. Okay, so the idea is you have a frequency that's a pattern, and again, if you're expanding the distance between 2 objects, then the frequency will get much bigger, the distance between the events, and if you're confining the space between the objects, then the frequency will get compressed. Alright, so that's pretty simple. And so they've used this as a reason to believe that the universe is expanding because everything appears to be moving away from everything. So everything seems redshifted, especially the further away objects. So close objects, they can look at them, say if a star in our own galaxy, for example, they can look at it and they'll see our relative condition, and it'll appear to be coming towards us or away from us because we're spinning in different orientations, and so we are either expanding the distance or contracting the distance. And then they can look at some things like binary stars, and they can kind of tell which way they're rotating because they can see which one's coming towards them and which one's moving away from them. But all of this depends on how they can see things, and the further away they get, the smaller the thing gets, and the more you can't isolate one side from the other side in terms of capturing the shift, the color of the light. But whatever. Alright, so the theory is that the universe must be expanding, that is, everything's moving, because things are redshifted a huge amount in their spectrum, and the spectrum just has to do with hydrogen having a certain pattern in a certain location in the visual light spectrum, and if that pattern is in a different location, okay, like this, it's shifted one way. If it's shifted the other way, it's shifted, blue shifted or red shifted. So again, that's all stuff people understand. All right. So the conclusion is that this is measuring your actual speed or your condition. When you consider that a photon is traveling light years through space, I mean, I don't even know how to define how far it is. I would argue that there's other reasons besides expansion of space to understand that light would be affected in traveling that distance. So we know that space has loose stuff in it. It has some gases, some loose hydrogen atoms especially, and they're spaced pretty far apart. So the more you have a vacuum, the more spaced apart. That is, the further apart the distances between any hydrogen atom. But you could argue the longer the distance you're traveling through that pattern, that would mean that the odds of hitting a hydrogen atom, for example, okay, even though they're sparse, it gets higher and higher the further the distance your travel is. And the simple argument would be is that you can account for redshift, especially redshift, by the fact that every single photon has to travel through the empty space, lots of it, and the empty space isn't purely empty. And the longer you travel, the more likely it is you hit a hydrogen atom along your path. And every time a photon hits a hydrogen atom, it would lose a little bit of its frequency. So its frequency, it's expanded a little bit. So the process of interaction with electrons means the photon will Compton scatter to some extent, and it will lose some frequency. So you could just make the argument that all you're really seeing is the consequence of light getting tired by hitting a certain number of having impacts with hydrogen atoms on its way. And yes, each photon will hit a different number of hydrogen atoms, but you could understand that over these incredibly long distances in time, they would all average out pretty quickly. So you wouldn't need many light years worth of travel before you'd end up with very consistent amounts of shifting because of the scatter. So it's very different than Doppler, because there's a cause that doesn't have anything to do with measuring emission or receiving of the bullets. The bullets are physically hitting something, and through the process of doing that, the frequency of the photon is being altered. So that explanation, in my opinion, doesn't have any counter theoretical obstacle. There certainly isn't any proof that hydrogen atoms won't do that to light, because that's already an established experimental fact. And the fact that they're there is also an experimental fact. And especially in those big clusters and the other things they sometimes have to see through, you could deduce that, of course, the light is going to get affected because you're seeing through other objects that are full of this gas, more dense hydrogen, and you're more and more likely to see the effect of the light being redshifted. So you don't need to believe the universe is expanding, and you don't need to believe everything's moving at gigantic speeds. You just need to understand that at huge, giant distances, it's likely photons are having some adventures on their way, that they're hitting something, and the something they're hitting is what's causing the degrade in their frequency. Okay, so that's all I need is a counter argument. I'm just saying that physics is just drawing a conclusion And they've used that conclusion to establish lots of things as facts. And I'd say the conclusion is suspect, that the red and blue shift that you're seeing, well, I'd say any blue shift you're seeing won't be explained by this, but certainly any red shift you're seeing would be. So they still have objects that they claim are blue shifted that are far away and moving insane speeds towards us. But the doubt there would be, you could question whether they know where the object actually is, whether it's billions of light years away or just millions of light years away. Sometimes they just can't tell the difference. So yeah, so that's enough of an argument for that, for the red shift. So now let's move on back to the energy arguments. Now, he says he's going to produce this video by the end of the week and all that kind of crap, and that'll be fun. But, you know, it really should contain something real in terms of an argument. And I just wanted to point out to him what people are saying to me. So, yes, it's a bold statement I'm saying, that there's no such thing as mv squared. Okay, that's a fable. We're still in drawing mode, right? Yeah. Alright, so I'll erase this. Okay, so I am saying there's no such, it's a fable. It's just made up. There's no need for it. It doesn't work in space. It doesn't have anything to do with thrust. It doesn't have anything to do with anything important. It's just nonsense. Springs and levers and pressure vessels and hydraulics all do conserve momentum. They conserve masses and velocity. And there's no 1/2 mv squared. There is no such thing. This is just a fable. This is the only thing that's right. This is the only thing Newton, Descartes, and Galileo believed in, was this. They got right answers with this. They don't need this crap here. And people like Professor Lewin say things like nature can screw with kinetic energy, but it can't finagle momentum. So it has to be conserved. So they're arguing that springs don't conserve momentum. Okay, and they're saying that levers don't conserve momentum. So they're saying that even though the two mass one distance and the one mass two distances, right, even though those two things balance perfectly and oscillate perfectly, if I put energy in here, okay, I will conserve kinetic energy, not momentum. So I will not get, mass and velocity here equaling mass and velocity here. I'll get 1.4. Okay, yeah. I'll get some other number out for the velocity here. So it will not conserve momentum. And they're saying the same thing about a spring. So if I drop something onto a spring, and we know that 4 times the distance, okay, will get you twice the velocity. I'm arguing it's twice the weight, and the other one would be twice the twice the velocity, twice the time, the important one. So 4 times the distance. Okay, so I drop something from one distance, and I drop something from 4, and I know I double the velocity that way in gravity. All right, and they're arguing that that doesn't work. Okay, that this double velocity, okay, they're saying yes, it'll have twice the velocity, but it won't compress the spring with the momentum. So the mass and velocity won't work, and it somehow, okay, the object won't have twice the capacity to compress the spring. They're saying it compresses it, some amount, that somehow the spring isn't regular, in the sense that they don't even believe in Hooke's law. So I don't even know how to properly paraphrase, because obviously one argument undoes another argument, and that's where it all falls apart. Now, I would argue that that's always been the case. It's the people have been arguing for 1/2 mv squared in the context where it clearly doesn't work. I mean, you can't have it both ways. Levers can't conserve both, and springs can't conserve both, because as soon as I change the masses of the object, go from big masses to small masses, I don't conserve the energy. So if we could make a Newton's cradle, the argument would be, that somehow those things don't conserve momentum either. You know, and to me it's a crazy argument, but whatever. That's their argument. So I'll show you a video where they're claiming this outcome, and I'd just like you to say that can't be right. Okay, it's not the physics you were taught, that you have to conserve the momentum, that the spring does in fact have to conserve the momentum. So theoretically I can put the 2 mass of energy into the spring, and it will lift the 1 mass with twice the velocity. Alright, or twice the momentum. That same momentum, but obviously half the mass has to go twice as fast, to conserve momentum. Alright, so let's go to this piece of crap video that has an obvious flaw in it, and but so I shouldn't bother because it's just so obviously flawed. But they don't think about any of this crap. They just post this crap, and it's just crap. Okay, where the hell is the video? Bon. Experiment. There it is. So he has a weird scale here. But anyway, so we'll just play him dropping one of these. Okay. And so they look pretty consistent to me. Both of them are just flopping around this 2 mark here. But what he's fundamentally doing that's wrong and stupid, is he doesn't realize that you can't have objects that are of different height and then have a place you're placing them at. I probably should have to go back to the drawing board. Well, yeah, I never left, so that's good. All right, so he's dropping. So, every time these experiments have these flaws, they don't care. They don't really think through any of this crap. Do experiments the right way, get right answers. So it's a dismal prospect. All right, so it's kind of a simple experiment. You drop the 2 mass, we'll say, just to make it easy, 1 unit of distance, and that means, it has 1 velocity. 1 velocity. So it's a 2 mass with 1 velocity, and then you're going to say the same momentum would be created by a 1 mass, moving 2 velocity. And to get the 2 velocity, you have to go 4 units of distance higher when you're using gravity to create it. So these 2 things should technically create the same momentum. So at the ground, they have the same momentum. All right. 2 times 1, 1 times 2. Same momentum. I'm arguing momentum is its weight. You can't evade it. So they'll compress the spring exactly the same amount because they have the same amount of momentum, thrust, pressure that they will be applying to the surface. And all you're changing is the mass versus the velocity. And they won't conserve kinetic energy. They'll conserve momentum. Now, they're arguing that the numbers are, in fact, different, and that there is more energy in the lighter object moving faster, and that it compresses the spring more. All right. Now, the problem with how he does the experiment is obviously you can see lifting an object that's shaped. This is the distance between you and the ground. But the real point is that the center of the mass is where you have to measure from. The distance is going to be a little bit more for up here and a little bit less for down here in terms of its falling distance, and so you have to find the center of its mass and say, well, you have to measure that distance. And so the center of mass would be a certain distance, but obviously if I stack objects on top of each other, well, then the 2 objects aren't going to have the same distance to the ground. This object's going to fall less far then this one up here is going to fall, obviously. So if I measure from this bottom, I'm going to get the wrong answer because I actually dropped the other one from this height. I didn't drop it from this height. So I dropped it from 20% higher, something like that, based on how much stacking I did. So in his case, he's stacking batteries. So clearly this battery was dropped from a higher height than this battery was. So they weren't dropped from the same 4 times the height. This one was dropped from much higher. Therefore, and this, when it hits the ground, is going to have a little more energy, a little more velocity, because one of the batteries is technically falling further in the gravity than the other one. So that is a failure, okay, to do the experiment clinically and properly. Now, the other problem, to their advantage, or however you want to describe it, is using a bizarre scale where the whole scale moves, like the base is down here and the scale's like upside down. And so to do impact measurements, it's really not going to work, because as you start making the speed differential higher and higher, you have to move the entire mass of the scale, whatever that is. Okay, now maybe it's not huge, plastic and all, but still you have to move all of the mass of the scale instead of this little part here. You're moving the entire scale with velocity. So obviously you're not going to get an accurate measurement, because you're moving a bunch of peripheral matter. And the faster you have to move it, the more energy it's going to absorb in moving the big object, the scale. So I've never even seen a scale with this configuration. So anyway, so amateur experiments, they're claiming they're going to prove that Hooke's law doesn't really work, that it's not consistent and linear in terms of the amount of compression in the spring equaling, okay, the amount of energy you're putting in, and this is twice the energy. Okay, whether we call it momentum or kinetic energy is the term, and obviously if it's kinetic energy, it can't be twice, because obviously, as I've stated, if I want to make the spring compress twice as much, all I have to do is the same work twice. The same 1 unit of work, and I put 2 objects on the scale and I get twice the compression. So obviously it doesn't work, in the sense that it's not conservative. I can't say the spring has 4 times the energy when it only took me 2 units of work to put the energy in. So I just mean it's there has to be a point where some statement is made. What is conserved in these mechanical systems? Is momentum conserved, or is kinetic energy conserved? And because clearly one argument means that all the physics teachers are teaching it wrong to say that there's any principle about conserving anything called momentum if you don't have to do it in a spring, or you don't have to do it in a lever, or all these other objects, that all these mechanical gear systems, if you don't have to conserve momentum, okay, that's a big difference than what they're teaching. But all of these cowards making videos won't make their video directed at conventional physics that they're disagreeing with. So it'd just be nice for a physicist to point out that conventional physics really does believe in conservation of momentum, and it isn't just something I made up. Yeah. Okay. So now we'll go back to the video. Well, we'll go to the video. All right. Where's the damn video? Yeah, there it is. Okay. So we'll just play a little bit of this dropping crap. But you can see that, so he has a 4-pack of batteries, and they're obviously stacked on top of each other. So when one falls, it's falling a shorter distance when the second group falls. It's a different distance they're falling. Technically, frankly, in the gravity. There's this one goes from, well, it lands in the same place, so maybe, I have to think about that, right? Because it has to push its energy through the other one. So, yeah, I have to think about that. It's not falling any longer, so it's the same amount of time, because it stops falling at the same place. So we'll never mind that. I'm just saying, okay, let's just take the video for what it's saying. Okay, so let's play a little bit of it. So that one looked like a pretty direct too, but you can't really, the slow motion isn't nearly slow motion enough. This isn't done with a high frame rate camera. So, mean, that reading was much higher, so who knows? You know. So these are what he says the outcomes are. So he's basically saying it's 1.7, and here it's 2. So that's pretty consistent with their theory, okay, that somehow there's more energy in the 2 batteries going twice the velocity than there is in the 4 batteries going half the velocity, and that the spring is measuring the kinetic energy. Now, I'm going to just argue that it's not possible for that to be true, but fine, that's what they're arguing. That nature can finagle momentum, but it can't finagle kinetic energy. So it's exactly the opposite of what Professor Lewin overtly said. And they don't care. That's not interesting to them, that they're debunking Professor Lewin. That's not interesting. Okay, so I knew it was first. We'll see if there's anything else here. Okay, I'll keep doing more of these experiments. Well, who cares? The thing here is, especially the 1 mass battery lands very unevenly and not in a straight line. So you're saying the results should be even, the double stack battery should have even more momentum. The objects that the other part is, it's just kind of obvious, his way of releasing these. Look how bent this ruler is, this, or whatever he's using to push these up against to get the distance right. I mean, it's you can see that, right? Yeah. I mean, it's bent. I mean, I don't even understand how that's your standard, is a bent ruler-y thing. Okay, so yeah, it seems bent in all those cases. Let's see. Oh, it seems awful straight now, though. When it's a higher distance, all of a sudden it's straighter. What's that about? So it's bent when you're dropping the 2 mass, but it's not bent when you're dropping the 1 mass. I mean, it's just pretty sloppy. So whatever. Whatever. It's just more of the same crap. These little crappy amateur experiments. I'm going to debunk the conventional notions with this crap. And I'm going to prove there's no conservation of momentum. Because there'd be no explanation for where the momentum went. Frankly. I can't think of one. Alright, I keep doing more of the experiment. The thing here is, especially with these 1 mass, they land very unevenly and not in a straight line. So again, he's saying that, oh yeah, I'll get even better results. I'll prove even better that momentum isn't conserved. The objects that I will use in the next are small plastic DVD boxes, whatever. So I don't know, whatever. Go ahead. I don't know. It doesn't sound brilliant to me. That sounds bigger. It sounds like you're going to have a problem with air resistance, but whatever. They land in a straight line when released with hand. Well, why don't you find a way to release them without using your hand? Why don't you figure out that the quick release or the mechanical release is better than using your hands to release things? And they land evenly, making full contact with the scale. Let's see what difference it makes. Yeah, whatever. Maybe you can do it with banana peels next time. Maybe you can, use carrot peelings. Maybe you can find something in the garbage to make the experiment out of. Whatever. All right, so the Gosling guy says, blow me down, that's it. Let's remember, for Gary, okay, now this is for Professor Lewin, okay. MV energy theory to be correct, both drops would have to register the same reading. Yes, Professor Lewin says that, yes, half the mass, it has to go twice as fast. You have to conserve the momentum. And he would argue that springs, because of Hooke's law, really are obligated to measure twice the weight. All right, it is clearly not the case. If I had used the same mass from the same location, it'd be twice the weight. Obviously, half the mass at twice the velocity is the same weight as a 1 mass at half the velocity. The 1 mass 2v, double the energy, would show a little more than the 2 mass 1v, because energy is squared of the spring's displacement. So again, that's a statement he's making. Okay, that's kinetic energy. All right, you can't conserve both. So we're really just arguing which one is conserved by springs. Do springs conserve momentum, or do they conserve kinetic energy? And obviously I'm arguing that they don't conserve kinetic energy. Hooke's law has nothing to do with it. Well, frankly, weight and pressure has everything to do with whatever's going to be called energy in the universe. So it's just absolute nonsense talk to say the laws don't have anything to do with it. This is why Gray would not do the simple experiment. So again, with this, I'm supposed to do the prove a scientific fact with this scale. yeah. Just that's the way physics should be done. It's just so pathetic. All right. He now has to make excuses to explain the difference again. I don't have to. All I have to do is say, okay, you're going to prove a fact, okay, that there's no conservation of momentum, because you're not going to be able to explain where the energy went. Okay, I mean, where the momentum went. So where did the momentum fail in this system? Where did you lose it? You're not going to explain that, so fuck you. Yeah. Difference again. Well done, Dispar. So he hearted that because, oh, thank you. I did another shitty experiment, okay, attempting to prove a mainstream fact wrong. Actually, it's already known in mainstream physics that energy equals force. And Newton said force equals momentum. You want to double something's velocity, you double the force. That's explicitly what Newton said. You're saying Newton didn't know what he was talking about. Okay, fine. I don't think you're going to be able to prove that. Even though it's not known to mainstream physics that energy equals force. It's already known to mainstream physics that energy equals force, even though it's not known to mainstream physics that energy equals force. I don't know what the fuck that could mean. Even though it's known to mainstream physics. Keep up with Gary is hard. Sorry, I don't understand that comment at all. So, complete rubbish and gibberish. Okay. Let's see, Eingeisling. The great irony is that despite his huge protestations to the contrary, he is the most unscientific person I've ever known. And you're the biggest, scummiest liar I've ever encountered. Any idiot who would sit there and turn an experiment completely upside down and do it exactly backwards from how the person described it. I mean, what the fuck? It couldn't have been more of a cheat. A disgusting cheat of what was argued. I mean, I argue how fast something travels across a scale impacts how much weight the scale will register. And what does he do? He puts the thing on the scale and then moves the scale and says, see, it doesn't change the weight. I mean, you can't cheat an argument that bad accidentally. So, I mean, obviously this guy has, he's such low character. But anyway, alright. So that's it for, yeah, the advancement of the subject at the moment. But I guess if the Michael guy is listening, I mean, the argument is that you don't have any evidence, right? There's no evidence of it taking 4 times the fuel to go twice as fast, okay, to accelerate twice as fast or to go twice as fast. So you don't have a single experiment showing that. Braking distance can be explained because that's gravitational friction, and gravitational friction isn't linear. That means it isn't the same no matter what speed you're going. So at high speeds the friction is very low, at low speeds the friction is very high, and it's through the amount of friction there is that you lose your energy. And losing energy is how we're measuring how much energy something has. So if I take a bowling ball and I roll it, it'll lose energy to the ground. And the rate at which it loses that energy is not linear. It doesn't go half the speed at half the distance. It goes half the speed at 3/4 of the distance. Because it's a Galilean thing, 1, 3, 5, 7. So that's why things roll 4 times further. if they're going twice as fast, is only because the velocity means they're losing less to friction per foot as an average. And it's the same reason why thrust in gravity works, in the sense that the faster you lift off, the less energy per mile of space you'll travel. So if you want to get into space, the idea is to get there as quickly as possible, and you'll use less fuel per mile. Your fuel economy goes way up the faster your liftoff velocity is. Those are the arguments. Okay, so the point is to come up with some kind of real physical evidence that demonstrates in any way that there's any such thing as 4 times the fuel to go twice as fast, or that 5-ton trains equal to, 5-ton trains going 10 miles an hour is the same energy, the same potential to do work, the same joules or watts will be produced as 2 10-ton trains going 5 miles an hour. That somehow you need 2 10-ton trains going 5 miles an hour to equal the pulling force or force of 1 5-ton train going 10 miles an hour. And if I just have 1 10-ton train and 1 5-ton train, that somehow in a tug of war, the 5-ton train will win. It will pull the 10-ton train going 5 miles an hour in its direction because it has twice the energy. That's the kind of physical evidence we need to debunk Professor Lewin's argument that momentum has to be conserved. Yeah. Okay. It really is just gotten so ridiculous. But anyway, let's see what we get. So that's enough of that. Yeah, let's just see. We'll just see if there's any new videos that they have produced, and leave it at that. So let's see if he's got his new CD one or whatever it is. No. Okay, this is the battery one. All right, let's see if the other asshole has anything. And we know the Brozo's out of the game for whatever reason. Okay, so he's just got his he calls this a prove KE. I don't know how he thinks proving twice the Clay's compression somehow is proving 4 times the energy, but whatever. Too silly. We should probably just play that again. Just how did he make this argument? So the Clay experiment shows twice the compression for twice the speed, not 4 times the compression.
Just to finish what I was saying about the Mythbusters experiment, Gary was saying, how do you explain that the one velocity squashed the clay sample an amount, and twice the velocity squashed it twice the amount?
Right, and it's supposed to be 4 times the energy, so somehow 4 times the energy doesn't squash it 4 times as much.
Twice the compression. And he says that's twice the energy, so where's your kinetic energy gone? Well, I think that's wrong. I think inadvertently, this wasn't the object of their experiment, but they actually ended up proving kinetic energy.
So you prove it by showing how it doesn't, something that does compress linearly, consistently, it squeezes out consistently. There's no physical explanation for why it would be harder to squeeze out later than sooner. And you're going to tell me that there's some reason. Well,
Because I think that this clay sample cylinder behaves similarly as a spring would.
Yeah, that's the whole argument. Frankly, if they used a spring, it would have done exactly the same thing. Twice the energy, twice the compression. Twice the momentum, twice the compression. I don't know. What's your argument?
And to squash this cylinder to twice as much would take 4 times the...
So again, there's just no evidence it takes 4 times the energy to squish things twice as much, and there's no, you don't have my argument. Okay, my argument is friction can make a difference. Friction can change how you lose your energy. Okay, so the faster something's moving, the less time it spends in the gravity per inch of surface, so there's less contact, less energy to lose, less ability to lose energy, because you have to lose it through friction. So if you have less friction per foot, kind of obviously you can get a lot of distance, okay, with losing less energy. And you don't have any counter explanation here. Why is it 4 times more work? Why does this get harder to compress like a spring? So he's saying somehow the spring is harder to compress. Well, harder to compress when, frankly, how can it be harder to compress when I just put another object on and it compresses it the same amount of distance? I put one mass on, it compresses. I put 2 masses on, it compresses twice as much. I didn't do any more work. I didn't do 4 times the work.
Energy. Like a spring would. I think they're very similar. So actually,
all right, so whatever. A spring will behave the same way because it's the same pressure, it's the same weight. So yes, twice the weight is twice the amount, and I'm just saying it illustrates that kind of obviously. Yeah, I guess I'm still not getting. You have to get it from his perspective. He really thinks that twice the compression of the spring is in fact 4 times the energy, and they can do 4 times the work.
They proved kinetic energy theory by squashing the cylinder twice as much. So
and if it would have crushed it 4 times as much, that wouldn't have proved it. Oh, okay, yeah. It's almost too ridiculous. All right, so that's his explanation. He's just saying somehow clay gets harder to compress the more you squish it out. So again, we're not compressing it in the sense that we're not forcing the atoms closer together. We're just moving them, pushing them away. Okay, so it's just expanding the clay. It's like pushing toothpaste out of a tube or something. He's saying it's harder to push it out, sideways pressure. Somehow the more toothpaste you push out, the more somehow it gets harder and harder to push out. Some kind of argument like that, which is obviously silly. Okay, so there's no point. Let's see, yeah, so it's only the one comment there. All right, so I'm sure Brozo hasn't done anything. Yeah, so we're never going to see the video he promised where, he redid the billiard ball lever experiment and, has this decisive evidence that it comes out 1.4, that somehow the twice as light object doesn't go twice as fast. That somehow levers don't conserve momentum. Okay, so they're saying that levers don't conserve momentum and that springs don't conserve momentum. They're asserting that's somehow obvious and we all should know that and every physicist should know that and they all should be teaching that, and instead they're teaching that you have to conserve momentum. So, it's just a huge inconsistency there. Now, I concede that what they're teaching is nonsense because you really can't choose momentum and then say there is such a thing as kinetic energy. You really have to believe in one or the other. You can't believe they're both real things. Okay, it's either conservation of momentum or it's conservation of kinetic energy. One of them's real and one of them's a fantasy. I'd say it's obvious that momentum isn't a fantasy and that it works. And it gets lunar modules to land on the moon. If you use the kinetic energy theory to measure your thrust, the energy of your thrust, you'll fail to land on the moon because it's fake. Okay, gun recoils have the same energy as bullets. It's not 1,000 to 1 difference. There's no physical difference in the universe in terms of your capacity, your wattage, your ability to move things. Whether you're 1,000 atoms moving 1 mile an hour or you're 1 atom moving 1,000 miles an hour, your ability to screw with the universe that has caused motion is exactly the same. That's the assertion. And it doesn't seem like there should be even any room for confusion, because we should have the experiments to prove it one way or another, and instead we don't. So in 300 years, they haven't produced any physical evidence that the 5-ton train going 10 miles an hour has twice the energy, that is twice the capacity to make watts of energy, as the 10-ton train going 5 miles an hour. Not a single experiment. Yeah. So anyway, okay, so that's enough of that. So we'll just do some chat and get the hell out of here. Alright, physics embraces bending, curving, and expanding space because it allows them to literally bend aspects of reality to conform to their ideas. That's the tricky part. I mean, I've met some, my father was a scientist. Now, he, an engineer, chemical engineer, technically. And there wasn't any woo in him, at all. I mean, he had no philosophical passion. Okay, so he just had no interest in any version of reality besides the one where, he puts on a funny hat and goes fishing, with his free time. So, I have to say I have a lot of the same character aspects that I'd rather just, play in the garden than do just about anything. And I really, simple pleasures kind of thing. But obviously I am more interested in all these philosophical subjects. But it is kind of strange because, you're saying, I really don't think, like, okay, Mickey Ayakaku, he's full of shit. Okay, he's full of just imagining Buck Rogers kind of horseshit. But, a lot of these other physicists, you're saying, I don't really think they give a shit about a wormhole or this or that. And, they're not really desperate to imagine themselves in a Star Wars adventure with their lightsabers or something. So I don't know, they're not, it just doesn't seem like, they seem pretty grounded. I mean, Feynman seemed pretty grounded. So I think it's just that they think the underlying premise that it's physics is ununderstandable, and the small universe isn't the simple universe. That's where it's different. They start with they buy into the ESP particle, and all the other kind of crap, and the idea of the gluon or something, the object that hits something and makes it move towards it, or some kind of completely backward notion of function. And once you build that into the model gets chaotic. And I think maybe they just like chaos. I mean, maybe they just like the puzzle to never be solvable, so they can keep moving pieces around. But it's hard for me to make a real psychological profile and say, why is all of mainstream, why are they all such dupes? I mean, why do they believe this crap? Somebody says there's gravitational waves and they just believe it. Some idea that you can make matter turn into gravity. I mean, actually literally turn into it. Can be converted into bent space. You can take a piece of matter and convert it into a piece, some kind of bent space thing. It's not like it makes bent space. I mean, like an emergent property. It actually becomes it. That's just too silly. Anyway, my MGH fails to explain elastic potential energy in a compressed spring. MGH fails to explain elastic potential energy in a compressed spring. MGH is accurate in the sense that 4 times the distance, it's a real thing that it's 4 times the distance. But yes, it's only right if you think distance is energy. So again, I just say, yes, we know that every time the G is in there, you really have to connect the G to time, because it's the units of time that decide how much energy you've collected. So you're collecting things, they're falling, and you're just collecting them. And it doesn't matter whether you move around while you're collecting them, it just matters that you're collecting them. So it's how much time you're in. Yeah, well, I've tried to explain that, and it just, yeah. But yes, no, MGH fails to get anything like a right answer, but MGH is just made to rationalize the kinetic energy theory. So I'm just saying, if they really believed in kinetic energy, they have to think MGH is right because it gets the right answer. In the sense that it states that there's 4 times the compression, but there obviously is, 4 times the energy, but there isn't. You fall twice as far, you don't have 4 times the energy when you land. It just doesn't happen. Because you're only in the gravity twice as long. How many times can I say that? That to me seems like that should be the end of the argument. All right. They fell the same distance. I don't know what that means. So, you're not making any sense there, Bruce. Okay, so you're not there's not much reason for me to put up with much of what you have to say, okay, if you're going to start this way. Okay, so you're not a flat earther. How did we get here? Who are we? I don't know what the we is. Electrons and Wi-Fi and everything. What kind of mush is that? You don't think we can get anywhere with wrong ideas? I don't think the Wright brothers fully understood the dynamics of flight. Okay, how exactly the air pressure was changing over the wing and all that crap. All they really understood was, hey, if I can get something going fast enough, this will work. Our models work. So we made some models and we pushed them through the air, and if we get them going fast enough with some kind of wingy thing, they will fly. Okay, so that's all they knew. And all they have to do is make this thing powerful enough and light enough, and it'll fly. So you don't have to have right answers to necessarily invent things. Okay, you don't have to have you don't have to have the concepts right. Let's see. It's ridiculous light, and we see the universe and all. It's ridiculous light, and we see the universe and all. I don't know. So difficult. I don't even know what you're talking about. So, you got to chat a little better than that, frankly. I posted a link in your last video to a space station experiment using... And I've played it in my fucking video. What the fuck? You don't watch any of these videos, all right? I already played this silly tennis ball, thing where, and I'm saying this is how silly the physics is. Instead of dealing with the real subject of momentum and kinetic energy, they're just doing this silly shit. So, again, there was nothing in the experiment demonstrating, well, why doesn't he hit something, he should be throwing something of a 2 mass into some other mass and see if he conserves the momentum. Because, yes, he will, right? And he won't conserve it in the kinetic energy sense, in the sense that you can, momentum's a vector and I subtract the reflection. That's not going to work. I can't believe that, people are just so... I can't believe you would post that video just because I posted it just to make fun of it because it's so fucking useless. So let me look in the comments. I didn't see any comment on my last video, but we'll see. All right, video 11, conservation of momentum. So again, you do it, you describe it this way without making any argument. What's your point of posting this piece of shit? Okay, and he says, hello there. Some of your videos might find interesting to discuss. Richard Goddard, space video blog, conservation of momentum. So here he goes again. Physics lab, collision and conservation of linear momentum. These are just going to show, yes, of course, but people could argue they're conservation of kinetic energy because they're not going to they're not going to do the conversion between things of different masses, and that's the key. All right, so let's go to some of these. It'll be fun, right? Yeah. All right, so let me get the chat out of the way. All right, and we'll go explore the fun links. See how many of them I've already played. Yes, so I already played this one, but we'll play it again, and we'll say, what does this show? What does this prove? Absolutely nothing.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time.
So this whole idea of a closed system doesn't mean anything. Obviously, the scalar and vector crap doesn't mean anything. Completely made up nonsense. All right. You're really just saying there's two relative objects, and all you're saying is between them the momentum has to be conserved. That things that actually interact with each other have to conserve the interaction. Okay, the energy can't disappear between the things that are sharing it. So whatever is part of sharing the energy has to be included. So obviously the air is included.
And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant.
Right, except if you put a spring on them. Okay. Or you bang them into levers. That's what, so they, again, the brozo crowd is all arguing that this scientist, this, NASA scientist, this astronaut, doesn't really understand. Because if I put a spring between the two objects, I won't conserve the momentum.
So, for example, these two balls, which in this case happen to be of equal mass.
Well, that's the case, right? So that's why this is useless. The equal mass crap just ruins the whole experiment. So he doesn't do anything with unequal masses, as we see. So this experiment doesn't show anything.
Second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other.
So just all kind of meaningless, blah, 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 blah. Doesn't show anything, doesn't demonstrate anything, doesn't do anything of any value whatsoever.
Objects will have half the velocity of the one initially that was moving.
Right, so that's the 10-ton train. So there, the kinetic energy. So he could just say to us right now, we lost half the kinetic energy. So let's just do that again. All right. So this one has some value. So this is their theory. Okay, he's going to throw this tennis ball, okay, and it has a certain amount of kinetic energy, 200, let's say, 200 watts of 200 joules of energy, and then it's going to join this ball, and it's going to leave, and the momentum will be conserved. Yet, half the kinetic energy will have disappeared. And obviously, no one's going to see where, oh yeah, it was a bunch of sound, and it was a bunch of this, and a bunch of that. No one's going to see any of that.
The total momentum will remain the same, so the combined objects will have half the velocity.
So he's got Velcro on there to make them stick together. So half the velocity, blah, 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 conservation of momentum, blah, blah, blah. And clearly, if you believe in 1/2 mv squared, you're actually physically arguing that somehow half the energy was converted into something else.
The one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle.
Right, so just keep tennis balls in your hand and then throw the tennis ball and you'll go the opposite direction and you'll be just fine. But yes, okay. So yes, we already played this video, but it is an illustration where it's even clearer, in my opinion, that this whole 5-ton, 10-ton thing, that I convert a 5-ton train going 10 miles an hour into a 10-ton train going 5 miles an hour, and then claim I lost half the energy. It just shows how ridiculous it is. But that's what 1/2 mv squared requires you to believe, that half the energy, it got really, really hot, something happened to half the joules of energy. They disappeared from the universe. They disappeared from the system. And just too ridiculous. All right. But it'd be nice if we did a lever experiment or something, but no. Alright, so we'll get rid of that and try the next one. So this is the same as this link, so we posted that link twice. Alright, the ultimate storytelling toolkit. It's a commercial, I guess. Physics lab. This is METU OpenCourseWare. Okay, I don't know what the fuck that is. Piano playing. Cool.
Fourth experiment. Collisions and conservation of linear momentum. Part 1. Elastic collision.
Now this is like Mrs. Chan or something. I've seen her videos before.
First, place the carbon paper and the data sheet. Before beginning the experiment, you need to check whether the air table is inclined or not. For this purpose, place one of the pucks in the middle of the paper and press on the P switch. Set the air table parallel to the ground using its supports. After that, set the frequency. In this
Alright, so at least I like this. So obviously the CO2 ones are probably better because they don't have these ropes, you know, pumping air into them. But anyway, I mean tubes. Because that probably creates a little bit of imbalance and, you know, some drag problems.
experiment, both of the pucks will undergo uniform motion with constant velocity. Press on the P switch while keeping the pucks fixed. The pucks should collide somewhere in the middle of the table. Launch them appropriately.
So we all know this is, again, same masses, blah, 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 blah. Not going to tell us much because when you're using the same masses, the KE fable, okay, will conserve the energy. The KE will be conserved and the momentum will be conserved because you're not changing the masses.
With a moderate velocity. You may need a number of trials before recording the data. First, you need to determine where the collision took place. The collision took place in this region. It is necessary to determine the velocities of the pucks before and after the collision in order to observe conservation of linear momentum. For this purpose, first determine the velocities of the pucks before the collision.
So, you know, all this, you know, and, you know, this is the kind of thing where, you know, in the 50s they were able to do these experiments better. Because, they just used a strobe, you know, and then you could just mark it all out with, you know, the same image showed you all of the motions and you could measure the distances and all that kind of crap. So this thing produces dots at some sort of consistent rate, and those dots are basically what they're going to use to measure the velocities. So the separation of the dots will measure the velocities, and they'll find out what the velocities are going in and then the velocities going out, and obviously they're going to be the same. So this isn't very interesting. Not interesting, and not interesting, and I guess that's all we're going to get. They're not going to change the masses. No, it looks like they put some Velcro on it or something.
If you are not going to examine rotational motion, you should prevent this rotation. For that reason, it may be necessary to make a number of trials before recording the data.
Okay, so we're not going to get the results of that one. So this is, again, the one where you put the two velocities in. You get the one velocity out, I'm sure. Conservation of momentum was achieved here. Blah, 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 blah.
Now you can analyze the data. You are going to repeat the procedure of...
Well, both of them are moving, so you're just combining the two velocities. So again, this one wouldn't be of any use in the kinetic energy argument. So, not very useful. I mean, both objects brought energy into the combined object, so you're not changing their masses. You're just sticking them to each other, changing their direction. So changing their direction doesn't use energy. Changing their mass would involve a difference in their kinetic energy. This looks familiar enough.
This is the lab for momentum, energy, and collisions. Okay, so the materials you'll need for this lab of course, are the instructions, and we've printed out a blank data table for you to record your data in. So you don't write in this. This is what you write on. You'll need a lab quest, of course, and if it's not charged up, a power source. You'll need your into the hole, and then that should allow the motion detector, the screw-in hole, to line up, and you screw that in.
Whatever.
Okay, so you're going to perform this experiment 3 different ways. The first way is both carts have equal mass, and you click to start your data collection, and then gently give the first cart a push. It'll collide and stick. Make sure they...
Yes, so again, this again will verify that it goes in with twice the velocity it leaves with 1/2 the velocity. So it had to collect the extra mass, had to distribute the energy across the extra mass. In doing that evenly, the momentum is conserved and the energy is conserved, and obviously the kinetic energy is not. Obviously, a big giant pile of kinetic energy is lost. Half the kinetic energy is lost.
Stick with the Velcro to each other so that it's a perfectly inelastic collision. That's one way you'll do it. You'll do 3 trials of that. Then you'll attach your 500 gram mass to the cart that is colliding into the stationary cart.
So again, it doesn't matter. So this will just change the numbers, but it still will be conservation of momentum, and kinetic energy will not be conserved. So another experiment doesn't really do much.
This cart will always be at rest initially. Record your data, give this one a push, and then you're going to repeat the experiment, but now this time the cart that gets hit has the 500 gram mass on it.
So now it's really going to lose a ton of kinetic energy, because now it's going to go away at a tiny velocity, because it's a big heavy object that's being added to the thing that has the energy. So a light mass with a high velocity, a very heavy mass with a very low velocity, and now we're going to lose, more than half the kinetic energy.
And start your collection, give it a push. Okay? So those are the 3 experiments you'll do.
Reduction.
You do 3
so the heavier I make this object, the more and more kinetic energy I will lose. I will conserve the momentum. The experiment will always conserve the momentum. It will always come out correct, in the sense that half the mass will go twice the velocity, sort of thing. Professor Lewin will be validated in terms of the momentum will be perfectly conserved, but the kinetic energy dramatically drops. So the closer I could get to the bullet in the gun, 1,000 atoms going 1 mile an hour and 1 atom going 1,000 miles an hour, the more you'll see this effect, where Newton's third law goes out the window. There's no equal and opposite reactions anymore. Nothing works, because there's this huge change in the energy. So he's saying that when he pushes the cart, let's say it had 100 joules of energy, both carts moving together with the increased mass now has 20 joules of energy. That just an insane amount of energy was lost, and that would go higher and higher and higher. Again, the percentages go way, way, way. And if I do the experiment the opposite way, if I could somehow make the cart lose mass, in the sense that the mass leaves pushing, giving back its energy. It gives its energy to the cart it leaves, so it is ejected. So if I could eject the mass from the heavier cart to make it lighter and lighter, but it has to eject the mass, that is, it has to restore the mass to zero, the velocity to zero, so it has to keep the velocity in the object that it leaves. So if I could make the cart where it just throws mass off, just drops it on the track, but drops it by pushing it to no velocity, then I'll start making free energy. Because I'll go from a slow cart, okay, with a lot of mass to a very small cart, very light cart with a very high velocity. So it obviously doesn't make any sense. The theory is crap. And, here we are. All right. Nice video. Where can I have the results? Oh, well, he didn't bother with that. Where can I buy these education material? Oh, that's what we need. Anyone else in Moat's class? So it's just about some guy named Moat in his class. All right, are we done yet? Oh, I think we got one more. I mean, it's fine. Look, I've done all this crap over and over again, so fine, do it some more. Whatever. We already know the argument. They say a 5-ton train going 10 miles an hour has twice the energy, okay, of a 10-ton train going, 5 miles an hour. The 5-ton train 10, twice the energy of the 10-ton train 5. They say it, but there's no evidence of it. Oh, another Bruce Yearney video, I'm sure. Alright, well this one doesn't mean anything. So this one doesn't show anything but the gravity argument. And obviously it's just about time here.
In this segment, I'd like to take a look at something I call the high road, low road track. As you can see, the tracks are the same length. They start at the same height, they end at the same height, but the paths from one side to the other are completely different.
Right, so the one the Mythbuster guy did with the 3 tracks is a better version of it, because it just sort of shows that there's a perfect, you can free fall and that'll get you your maximum velocity. And the whole idea is you're trying to keep the free falling as much as possible, all right? And you don't want to lose too much energy to turning it going this way. So you're converting energy going down into energy going sideways. And the idea is that you can do that conversion at a peak efficiency. So there's a perfect amount of quickness to getting to the high velocity. The ball wants to spend, to get to the other side, you have to figure out that you want the ball to be going the fastest it possibly can as soon as it can. So if I drop it straight down, it doesn't go sideways at all. So that doesn't work. So I'm trying to find where's the medium between where I'm pushing it, I'm converting this direction into this direction, and there's a perfect efficiency where I do that conversion with losing the least to friction and getting to the highest velocity possible, the quickest possible. And that's all it really is about. You don't want to increase your velocity late. You want to increase your velocity early, because then you'll be traveling the distance at the higher velocity. Okay, so that's the idea.
This one takes the shortest possible path, which is a straight line. On this track, it starts and then it goes down for a distance, and then the ball has to come back up to get to the opposite side. So the question is, if I were to release the balls from the same height at the same time, which track would get the ball over to the opposite side the quickest? Now, before we actually do this, I would have my students come up with a hypothesis.
Yes, right. The faster you can get the velocity. So this one will obviously have a much higher velocity because it fell further than the gravity. And so it'll travel this whole straight path much faster than the other one will. And obviously the energy in is going to be the energy out, so it'll not have a problem going up higher because you dropped it from higher. So he could make that even more dramatic, and he could drop this even further and even further and even further and keep increasing the velocity.
Give me an explanation of why they would pick one track over the other, or maybe they're going to get over there at the same time, but they need to make a prediction before we try it. So let's take a closer look.
So obviously a lot faster. Not quite twice as fast, though. Anyway, because he didn't go 4 times the height difference. So I guess that's what he... And it's only the straight part of the track isn't very long, obviously, here. So the advantage isn't for very long. The speed advantage. Alright, so this is about building it, I guess. Who cares? Oh, here, see, he could make it even deeper, and he did.
Even though the ball is dropping to a lower distance, it's still able to get it to the opposite side quicker because more of its potential energy is changing into kinetic, so it's covering that distance.
And he means kinetic versus potential. He doesn't mean kinetic versus momentum.
At a higher rate of speed.
Right. And I guess the perfect would be the circle. The parabola. Yeah, maybe the parabola would give you the least amount of friction and the highest amount of velocity. I don't know for sure. But let's see if he does that. No. Okay, he goes back to that track. And then he does this track, which shouldn't make any difference. It's just such a small amount of time that you're at the peak velocity, and it's such a small amount of time, it's not going to make as much difference.
That the energy is simply coming from me lifting it up at the very beginning, and the second track, lifting it to the same height, it's dropping down, coming up, dropping down, coming up, dropping down, coming up, dropping down, and finally coming up. It's covering a considerable more distance in this track than it is in this one. Is that going to be enough to finally get the balls to match once they get to the other side? So let's try it, see what happens.
Yeah, so barely faster, because this distance is tiny. That's the only reason why it's not much faster, is that if he could expand this distance here at the bottom, the more time he spends at the bottom is the only place he's getting an advantage, mostly. So this is the part that matters. And there's a very little of that. So if he could expand this part out flat, and this part out flat, and this part out flat, and this part out flat, then he would gain more advantage because he would have a higher velocity. Alright, so slow motion doesn't do much for this experiment, but whatever. I suppose it's pretty...
So even though this track has additional distance that it has to travel, it's still able to get the ball over there quicker because as the ball drops down to a lower distance, it's changing more of its potential energy into kinetic, and that's going to allow it to travel this distance further or faster than...
Yeah, so again, it's just about the velocity, and you're just increasing the velocity by increasing the amount of gravitational energy you're taking advantage of.
And the track that's up here. So these are my high road, low road tracks. I hope you found them interesting, and come back and visit again because I have other things I'd like to show you. Okay, thank you. Bye.
All right, so blah blah blah. Not terrible, but not terribly useful either. Doesn't provide anything new, so that's the problem. It doesn't give us a new bit of experimental evidence that could in all ways be proven to be collecting energy in any real sense, showing us that it really does take more energy. All right, let's see. Shouldn't be difficult. Nothing to do with getting a point, just noticing we are currently in the dark. It has nothing to do with getting to a point. Okay, well then just go away. I really don't think it's at all complicated, frankly. And so you want to believe life is mysteriously and all that crap, go ahead. But it has no interest to me at all. This is not that complicated a puzzle. Just noticing we are currently in the dark. I don't know what that even means. Yeah, your sentences suck and your point is mush. Okay. Anyway, good night, LOL. Good. Goodbye. All right, Bruce. If they throw them at each other with the same speed, they would lose all their KE. So again, we know there's no losing of the energy. It has to be converted into something. So obviously, two tennis balls collide and you force them to stick to each other. Okay, there's going to be vibrations and movement and maybe spinning, and something's going to happen. Because you really can't make the energy just go away. Obviously, there's a lot of stress. Let's say you were connecting two things with Velcro. Obviously, if I bang one thing into another thing, the sticking isn't going to cost the Velcro much. But if I'm banging two things in and crashing them into each other, that point of impact is going to have to do something. So the car collision is probably a better way to look at it. I bang two cars into each other. It would be ridiculous to say the kinetic energy disappeared. Okay. I mean, you know, whether you're talking about momentum or kinetic energy, it obviously didn't disappear. There's not zero momentum. There was a whole bunch of energy used to break the two cars, to throw their pieces all over the place, to crush them. So, I'm just saying, you know, the energy doesn't just disappear. So even if I can make the cars out of titanium, and in some ways force them not to separate, you know, not to bounce off of each other. I'm just saying you got to know that something has to do physical work. Work has to be done on something, because there's wattage. It has to go somewhere. The fact that you have to conserve energy should be something everybody agrees on. The argument is what are you conserving, KE or momentum? Physics is arguing the momentum is conserved, and they can finagle kinetic energy. They can just fuck it. That's sort of their argument. That KE is sort of fake, virtual energy. It's not the kind of energy you actually collect and do something with it. It's just fun. So, I guess that's it. Anything else from anyone? No? If not, I'll just get out of here. We really aren't, you know, the argument's just not going to get advanced by these crappily done experiments. So, that's a black hole from which there is no rational escape. You know. It just is kind of funny that they are actually arguing that twice the weight is 4 times the energy somehow. Even though it doesn't take 4 times the energy to create twice the weight. It only takes 2 times the energy to make twice the weight. And yet, it's 4 times the energy. I mean, the fact that they won't concede, you know, that can't be right. There's something wrong somewhere. You know, it makes the whole conversation just a little bit ridiculous. I mean, if they won't concede that they have to explain that, you know, Twice the weight lifted, twice the distance makes 4 times the energy. Yes, I'm just understanding. You're moving one weight, and you're doing it twice. You're not lifting twice the weight, twice. Twice the weight is 4 times the, yes. But we're not doing twice the weight. We're lifting one weight, one distance. And then we're moving one weight, one distance. One weight, one distance. One weight, one distance. That doesn't equal 4. That equals 2. It just getting hard. No, it just doesn't make any sense. One weight, one distance. One weight, one distance. That means I did 4 units of work. So he just did it again. 2 weight, 2 distances. So he's again just saying that the fact is that the second weight is somehow magical. The first weight is only this much movement on the scale, and somehow when I do the second one, I did the 4 part. I did this much more work. I pushed on the scale much harder somehow with just putting the second weight on. It's just such a silly thing to do. Sorry, it's silly. They're all ones. I mean, saying 2 ones, okay? They're ones. They're ones. They're ones. Yeah, I don't know. How is this hard, he says. Okay, I'm just saying, I'm just saying, it doesn't make any sense to me for you to say that I can do one piece of work. This is 1 unit of work. You get that? It's 1 unit of work. Where you can see this is 1 unit of work. 1 unit of work. 1 unit of work. I do that twice and I get 4 units of energy. That's what you're saying. Okay, so you can do your 2W times 2D equals 4E. No, I did 1 unit of work. 1 unit. 1 unit. Only 2 units of work. How can 2 units of work equal 4 times the energy? This isn't hard. How is this hard? I'll ask you the question. How is this hard? This is a unit of work. Lifting one object this high. And the fact is, the second time I don't have to even lift it as high, so I don't have to do as much work to get the second one on the scale, actually. So it's going to be 1 plus, 0.85. So I do 1.85 the work, and I get 4 times the energy by your theory. I'm just saying, I mean, how is this hard? This is 1 unit of work. Okay, now I'm going to do the same thing and just leave that work as done. I did it. Now I'm just going to add another unit of work. How can that be 4 times the energy? I only did 2 units of work. It's going to be 0.05 plus 0.15. That doesn't mean anything. It's the 1/4 3/4 ratio. That doesn't mean anything. How does this second pen weigh 3/4? I guess I could use batteries because I don't have any more pens. How is this different? This work was the same work as this work. Same work. And it's only twice the compression, by the way. So it's only twice the weight. And you're saying twice the weight is 4 times the energy. Twice the weight is 4 times the energy. How can I make any sense out of that? The first tiny compression of the spring takes close to 0 force. So what? We know it's not zero force, so you can say close to zero force. Who cares? We know it doesn't weigh zero. The force gets bigger in proportion to the compression. So again, you're just saying shit. Yeah, yeah. Hooke's law is on my side, not your side, retard. Hooke's law says twice the weight, twice the energy, twice the compression. So the average force over the compression is half the force at the bottom. So again, just more bullshit. I'm just saying it's 2 units of work. You can't get around this is only 2 units of work. How can 2 units of work be 4 times the energy? So just keep evading my argument. No wonder nobody wants to debate you. I don't understand. Just whine some more. This is your debate? How can 2 units of work be 4 units of energy? I mean, it doesn't matter how I get them on the scale. You know, I can just roll them onto the scale. I can just slide them from a surface and just use a little tiny bit of energy to get them on the scale. And you're saying I'm doing work that somehow I'm going to get back from the spring. So, well, it makes it more complicated, because obviously you're just taking advantage of the gravitational distance, okay, and saying they're going to stay at that distance. So the fair measure is to measure it from the spring's compression point of view. So from the bottom of the spring, you lift it up to the top of the spring. That's 1 unit of work. You take a second object, you put it on top of the spring, that's 2 units of work. Again, you can't get around it. It can't possibly be sensible for you to argue you can do 2 units of work and get 4 units of energy out. I don't know, they lost energy? I don't know about this losing energy, but whatever. The point is they only go the 2 units of distance. You're sitting there saying it's 2 units of distance. Yes, they weigh twice as much. The spring compresses twice as much for twice the weight. Where do I need any 4s in here? If you want to repeat the experiment, you would have to lift the 2 units of weight back up 2 units of distance. That's 4 units of work. Yeah, the fact that you're going to do it less efficiently than, free falling on a scale. So he's saying that it takes 4 units of work because the spring compresses further. But again, I had that extra unit I didn't use. I don't have to lift it as high, so you can't make that argument. The first unit of work, if you're going to make those arguments, then I'll just make the argument that when the spring compresses, I don't have to lift the second object as high because the spring already dropped down. So the second object only did half the work. Alright. Oh, you nearly understood there. I saw it. It looked like panic. Yeah, whatever. You're showing yourself here, okay? Everybody can see you for who you are in your arguments. And how you haven't explained how 2 units of work can produce 4 units of energy. How 1.5 units of work can produce 2 units. these little nothing comments. Right, that's why it's 1/2 mk times 2. So just more squared. I mean, it isn't. So you can just keep saying that's the formula. I can show you videos where they tell you, no, you don't have to do the equation that way with your halves and squares. There's nothing in this. Okay, you showing me this 1/2 mk squared is just telling me 1/2 mv squared. I'm saying, no, that's not true. You'll never produce the experiment. You'll never show it taking 4 times the fuel to go twice as fast. You'll never show any fucking experiment where this is really true. You'll never account for the 2 tennis balls sticking to each other and moving off at half the velocity, and you'll never explain where half the energy went. You'll never show the 10-ton train losing decisively the tug of war to the 5-ton train going 10 miles an hour. You'll never show any of this. You just keep saying it, saying it, saying it, and you'll have no evidence you'll ever produce. Levers can oscillate with 1,000 times more energy on one side than the other side. That's your theory. It's ridiculous. I mean, if you had this all pat, you'd be able to make a reasonable argument, but you don't. See, I mean, you gave me this 2 thing, right? And it wasn't accurate, right? Because if I compress the scale with 2 objects, when I lift off one, the scale will rise, okay? And the second one, I don't have to lift as high. I mean, so I could make my argument that way. But I'm just saying, you didn't consider that. You just typed this crap as if it's accurate. And it's not accurate. That's the whole point. You're not acknowledging that there's a subject here, that you really don't have any right to just make your declaration and say it's been proven. It clearly hasn't been proven. It clearly hasn't. You haven't compiled evidence. You haven't even thought it through very much. I just keep saying that explains the half in front. It's a useless mush. I thought you were arguing against the squared part. Both parts are useless. They mean nothing. The half was added because they were obviously getting preposterously wrong answers. Okay, their numbers of joules they were coming up with were way the fuck off, so they had to put the half there to make newtons connect to joules. I mean, without the half, you'd be arguing it has 4 times the energy. You know, the 5-ton train going 10 miles an hour has 4 times as much energy. I just don't know why you're so convinced and so glued to a theory that just can't make any mechanical sense. I mean, how do you think the elemental universe functions this way? I mean, how do you think the elemental universe sees the difference between 1,000 atoms going 1 mile an hour and 1 atom going 1,000 miles an hour? How can you exchange the motion in the universe if you just had electrons in the universe? And you were just saying that I have 1,000 electrons going 1 mile an hour in this system. And I have 1 electron going 1,000 miles an hour. How can you move the motion, the energy, into the system and in any way calculate that you have 1,000 times more energy with the one atom moving 1,000 miles an hour than you have with 1,000 atoms moving 1 mile an hour? How could you make the exchanges, the banging into things? How could any of that make any fucking sense to you? The one atom moving 1,000 miles an hour can only make 1,000 atoms move 1 mile an hour. It can't do anything more than that. If I bang it into 1,000 other electrons, and each time it loses 1%, of its energy, 1/1000th of its energy, it gives away 1/1000th of its energy. It can only give away the 1,000 to 1,000 atoms or electrons. I just don't know how you can. I just don't know why you're defending this crap. You have no evidence. You can't show me any evidence, and it doesn't make any sense. 1/2 is a constant. Well, who cares? It doesn't affect the ratio of the energies. Well, of course, it doesn't affect the ratio, but it affects the comparison between momentum, newtons, and joules. It certainly affects that. You can't exchange one at 1 mile an hour for one at 1,000. Yeah, you can't make a slow thing give its a fast velocity, but you clearly can make a fast thing give a slower velocity. And in every one of those cases, okay, you're going to conserve the momentum. Obviously, something can't give a push that it doesn't have, okay? Something going 30 miles an hour can't push something 60 miles an hour. So it obviously can't give away all of its energy because it can't make a lighter object go faster than it's going. So it has to keep some percentage of the energy. But I'm just saying, if you went through the bowling pin analogy of a bowling ball, an 8-pound bowling ball hits the pins, how is it going to distribute the energy? It's going to make the pin go at 8 miles an hour, isn't it? And the 16-pound ball, the 8-pound ball going 16 miles an hour, it's going to give the pin 16 miles an hour. So it's going to give away to each pin, the first 3 pins it hits, it's going to give them a lot more energy. So the first 3 pins are going to leave with a lot more energy. But the last 3 are going to leave with a lot less. Okay, so do the calculation. I did it. There's no way it works, right? The kinetic energy ends up... You can't make the 8-pound ball going 16 miles an hour actually move more pins, more distance. You can't make it happen. All you can do is change which pins get how much energy. But you can't change the fact that the momentum is going to be distributed evenly among them. You're going to conserve the momentum. And in conserving the momentum, that's the energy. You won't be able to maintain the extra speed of the pin because, yes, it's going to hit the wall and all this other stuff's going to happen, and the energy is going to be dissipated into the small units again. It's the same number of small units. One 1,000th of its energy is more energy than each of the 1,000 at 1 mile an hour. Says you. There's the whole point is there's absolutely no evidence of that. It doesn't work in space, so we concede that it won't work in space. So if you do this in space, okay, you have a spaceship and you're flying in the spaceship, and we'll say this is the 1,000 atoms going 1 mile an hour, and this is the 1 atom going 1,000 miles an hour. I do it in space. What do you think is going to happen? I do both of these things at the same time. The ship isn't going to move. There's not 1,000 times more energy or joules or watts that I've let the universe have on one side than I let it have on the other side. It's the same amount of production. And so just say you don't believe in Newton's third law. Equal and opposite. You don't believe that the pushing power, to push the 1,000 atoms, I didn't have to push harder. I mean, to push the one atom going 1,000 miles an hour, I didn't have to push harder on it. I'm not going against you there. Yes, you are. You're clearly... I'm just saying, if the ship doesn't turn, it's not real fucking energy. Can you understand that? It can't possibly be called something real if it can't make the ship turn. So if the ship doesn't turn more when you shoot the bullet out one side and you shoot the gun's recoil out the other side, if the bullet side doesn't mean the ship turns radically because there's 1,000 times more watts, more heat leaving... There's more heat leaving this way than left that way. How can you fucking make that make sense? That somehow 1,000 times more heat went this way, and yet my ship didn't turn. There's no point in talking about it. I just sit there and use this baby talk and tell me momentum is something different than, okay, energy. It's just idiotic. The dispute is from the very fucking beginning, okay? Leibniz wasn't saying momentum wasn't energy or any of this crap. He was saying it wasn't the right answer. Okay, it didn't have any meaning. The only thing that has meaning is this mv squared crap, this living force. You have to pick a side here. There's no coexistence between these things. They're not compatible. Anytime I change the masses and I go from light masses to heavy masses, your theory says I'm making energy. All right. Do you understand how scientists are getting energy from thin air? I don't know what the fuck that means. If you know what I'm referring to, I can link an article. It's not an article from a real thing, so fuck you, okay? There's no thin air fucking energy, so fuck you. Too silly, scientist. My ass. Alright, then we can resolve the whole argument by ignoring anything to do with energy. Fuck you. Energy is the most important subject in physics. There is no physics without the word energy, for fuck goddamn sake. There's no motion, there's no action, there's no anything. Energy is the subject, fuckhead. Oh, God. Just use momentum. Ignore energy. What's the problem? You're asking me that question? I don't understand. You're the one creating the problem. You're saying there's this extra stuff, this extra energy, okay? You're saying there's this real energy called kinetic energy. I'd love to ignore it. I'd love to pretend it doesn't exist. I personally don't need it, so yes, I can do that and function perfectly in the world, understanding conservation of momentum. I'm just saying, what good is this kinetic energy nonsense but creating a bunch of fake particles? So yes, all of particle physics is based on 1/2 mv squared. It's all a bunch of fake energy created by fake experiments, frankly. Experiments where they think they're making free energy. And that's why they have to increment neutrinos and all this other crap. It's because they don't understand that they didn't make free energy. I mean, it's just like saying ignore the fact that other people believe in Jesus. Oh, it doesn't have a consequence? You people having the wrong answer doesn't affect me? Of course it affects me. The whole point is to have some respect for the fucking goddamn truth. If your energy is virtual and a figment, then why the fuck are you believing in it? If it doesn't do real work, why argue in defense of it? If it can't turn a spaceship, it's bullshit. So will you just admit that much, even? That would be the purest experiment of whether something has energy, right? Is the simplest experiment you can do. And the argument is, will you gain more velocity in your spaceship if you eject a bullet or you eject a recoiling gun? And if you'll admit that no, you won't gain any extra velocity by ejecting the bullet, at the required speed versus ejecting the gun at the required speed. Let's just make it 1,000 times difference. 1,000 atoms going 1 mile an hour, one atom going 1,000 miles an hour. Will you admit that those two things will get you the same velocity in your spaceship? Okay, so you're conceding the argument, in my opinion. You're conceding that the most pure experiment you can do in space clearly demonstrates there's no extra energy. Apparently they run air through very small holes drilled, and it somehow produces energy. I'm just not going to argue with you. It's just, as soon as you just talk about air moving, fuck you. It sounds BS if you ask me, but people claim it works on a small scale. Well, I'm just saying, there's lots of people making lots of claims on the internet, idiot. If you sit there and waste your time thinking they're making any sense, then you're wasting your time. There's people selling all kinds of devices that are supposed to make water and do this and do that. There's people saying they've got fusion, when they don't have anything close. So yeah, some scientists talk a lot of shit, but that's not really the subject. The subject is the textbook science is shit, and that's the part I want to argue, is the textbook science. I don't think anyone will argue against that, so that's really funny, because they are arguing against it, frankly. So I'm just saying, you're conceding the argument, aren't you? Aren't you conceding the argument? If you can't move your object in empty space with your energy, your kinetic energy, if you can't use kinetic energy to move things, then how could it possibly be considered energy? Yeah, well, you know what? I mean, hydroelectric is about humidity in the air, technically, right? I mean, it's just silly to call that, free energy, because it's obviously the, convection on the surface of the Earth is doing the work, and we're just stealing some of it, It's not energy from nothing, it's energy from something. All right, let's see. The bullet and the recoiling gun both hard energy, and they both move things. Well, I'm arguing clearly you're arguing that they move things. We're talking about heat and watts and joules. We're talking about real energy in the universe, okay? So you can't play this game. Your bullet has 1,000 times more joules. Are joules real things? Or is the wattage real? If the wattage is real, then it has to be able to move the ship. If it's not real, then it doesn't move the ship. So I'm just arguing that you're playing a word game here. It is a fact that it takes 1 Newton is 10 joules. I mean 10 newtons is 1 joule. I mean, these are mathematical facts. You can pretend it's not the same thing, but the fact is it always works. So why are you making this argument that somehow your definition of energy can be this mushy, and you can say that, no, it's not really those joules of energy produced, when it is? A Newton is a weight, okay? It's not a weight over a distance. It's a weight, period. So let's not, you're just going to keep playing games. Let's stay on the subject. Just forget I said anything about newtons. Let's just get to your point, okay? A joule is a watt, right? Everybody knows a watt is a real thing. It converts into real things called heat units, BTUs, lots of stuff. So you can't fuck with it and pretend it's not a real thing. So I'm just saying, you're saying the bullet is the production of 1,000 watts. Let's just say the joules are watts. And let's just say, okay, it's 1,000 watts with the bullet. and it's only 1 watt with the recoiling gun. And you're saying it doesn't change how your ship moves. Somehow you produced 1,000 watts into the universe on one side of your ship, and you only produced 1 watt on the other side, and somehow your ship doesn't move. Alright, so you're just going to keep playing games. Alright, fine, fuck it. Everything is in a unit of time, so it just doesn't make any sense. I mean, a joule is the weight of a stick of butter, traveling 1 meter. So what? We know it's an impact energy. We're talking about movement of matter. Yes, matter isn't in a unit of time. Its movement is. I mean, you're just playing games. I mean, what is imperfect about the spaceship experiment? You're saying the experiment isn't showing your energy. You say there's more energy going out one side of the ship than the other side, but the spaceship isn't showing it. And I'm saying you can't get a more perfect experiment. If your energy can't move the spaceship, it can't do anything ever. I mean, let's understand, the spaceship could be 1 atom. The spaceship could be an infinitesimally small thing. You're just basically saying, no, it doesn't move based on kinetic energy. It moves based on momentum. Well, if that's true, then there is no kinetic energy. It's just nonsense. Because if it can't move matter, it can't do anything. It can't do anything called energy. Energy is moving matter. If you're not moving matter, the energy doesn't exist, essentially. Energy isn't doing, a photon isn't doing work while it travels through empty space. Okay? It's only doing work when it hits a piece of matter and causes it to move. Well, I don't think you're going to be able to explain that. So I'm just saying, let's just leave it at that, okay? So he's made the argument and said his energy can't move a spaceship. So I'm navigating in space, and I can't use his theory, okay, to move my spaceship. His energy theory won't work. He's conceding it won't land you properly on the moon. So if you try to land your lunar module on the moon and use his KE theory, depending on what you're throwing out of your exhaust, you're going to get completely different results in terms of how much movement it caused the lunar module. So you're not going to land on the moon if you use KE. And if you use momentum, you will. So if he'll concede that momentum will safely land you on the moon, okay, understanding what particles did you eject from your ship at what speed, and as long as you have that data, you can accurately land on the moon. And without that data, if you use some other KE data, okay, of joules of energy, you're not going to land successfully. He's conceding the point. You would use the energy equations to calculate how much fuel you need to put on the rocket. It's just more nonsense. I mean, I did do the research, right? There's a few videos where a guy explains exactly how the computer that NASA uses and how they had to store it. And, it was a very small amount of memory. And there's no KE formula in there. Okay, they weren't measuring KE. They weren't measuring joules of energy. They weren't measuring fuel equations in any other form than understanding their fuel as momentum. They understand the fuel, a certain pounds of fuel equals a certain capacity to create velocity in particles that they're going to eject. And it's just the velocity of the particles that are going to eject that decide how much the ship moves. What? They presumably loaded the fuel before takeoff. Why would that calculation be on board? Again, it's understood as a calculation of momentum. It's not understood as a calculation of joules. Because they know the joules number changes. The the number of joules you'll get out of the fuel depends on whether you're throwing bullets or throwing guns. Don't you understand? The momentum number is the same whether it's guns or bullets. The joules, the Newton's number is the same whether it's guns or bullets. The joule number is completely different depending on what I shoot. If I shoot big molecules, I have no energy. If I shoot little stuff fast, I got tons of energy. That's the truth. So anyway, I'm just saying. So we have him conceding his theory can't move a spaceship in space. The most clear and clean energy experiment you can do theoretically, right? There can't be a more clean experiment you can do than to have a spaceship in space and you're going to move it, an object in empty space and you're going to move it. Can't have a cleaner experiment. And he's basically conceding that 1,000 watts of heat out one side will do exactly the same amount of moving of the ship as 1 watt out the other side. So, that's some value to these interactions. I guess I can just make this the cleaner argument. Just say, just if you can't move a spaceship in space with your energy, then it can't really be called energy. It's just lying to say you have an energy theory that completely doesn't work in space. It's stupid to say one has 1,000 of something going one way and one has only 1 of something going the other way, but they have exactly the same effect, and say that they somehow have different energies. They can't have different energies if they have exactly the same effect. It was funny when I threw that one at AB Science, a long time ago. I wonder what happened with him. I guess he's working hard or something, doing real physics. But yeah, he kept saying things like energy doesn't have anything to do with thrust or something. And you're just like, what are you talking about? It's like the most elemental use of energy there is thrust. How is thrust not a valid way of measuring energy? Look, it's one or the other, all or nothing kind of thing. There's just no way. There's the fake lie that there's a compatibility. It's like wave particle. There's no wavicle. Okay, it either is a wave or it is a particle. Come on, you can't play this game. And this game is the same argument. It's either KE or momentum. Both of them are not viable, compatible theories. They describe the same circumstance entirely differently. How could they both be right when they don't describe the same elephant the same, as an elephant? Off topic, but are you aware of anyone who agrees with you who is making videos? If I was, I'd be pointing it out, wouldn't I? Be, hey, go watch his video. It's really great. He's making my arguments even better. Yeah, that'd be so super. I wish. I mean, you can make some arguments that at least on some of the topics, you could argue that Bill Gates makes some good videos now and then about just how batshit crazy physics is, and how you can make a good argument about how they have shit for evidence. So somebody can at least make that point, that they haven't proven any of this shit. They just tell us what the truth is. They don't show us what the truth is. But, yeah, no, it is really sad, frankly. I mean, I'm sorry for all of you. I mean, I'm sorry you're so dupey and stupid. I mean, geez. I didn't really know how bad physics was. I mean, I knew it was bad when I went to school. I related it. I mean, I actually did technically. I didn't technically. I untechnically failed physics. But it's because the teacher was a fucking nerd. And the other problem was that, it was a personality issue mostly. But yeah, to me, it was... They just turned something that could have been a fun, good subject into crap because they started drawing all this wavy bullshit. I mean, the first time they drew that photon, that was in grammar school, I was like, fuck you. And then when I saw radiation in a cloud, we built little cloud chambers and I actually saw the little shit flying off in little straight lines. It was like, why are you telling me all this horse shit when, look at this, how the fuck are you turning this into waves? You fucking retards. So, I had this idea that, yes, okay, they talk some shit in physics that doesn't, I couldn't say they were wrong, but I felt like this isn't, I can't do this. This is religion. I mean, this was like doing your catechism or something. I can't take this seriously. So I sort of, can't say I lost interest because I loved mechanical things and, I fixed cars and I did lots of shit. So I like to understand how things worked, but yeah, it just ruined physics. And then later, I started hearing about this two-slit shit and this fucking woolicles and superpositions and entanglement, and that's when I got re-interested in maybe arguing some of this crap. I imagine this is directed at me. What's your definition of energy? I mean, isn't that too silly? I mean, it's like your definition of wet. Fuck you. It's as elemental a word as you can get. Energy is the movement of matter. There, done. I mean, obviously the thing that moves the matter has energy. The force is. So force is energy. Okay, because it's basically, again, little bits of stuff moving at a very high speed. Oh, spin, yes, spin and charm. Isn't that a graviton? It's just too silly. Strings, quantum entanglement sounds like nonsense, but classical mechanics seems solid to me. Well, I don't know why you're doing all this arguing then. Because all that stuff is a direct attack on classical mechanics. They don't use classical mechanics to deduce any of their, to do any of their deductions. They assume waves, they assume kinetic energy. The message didn't get through, not sure why. So what's your theory about why nobody agrees with you, and is it a conspiracy? Yeah, it's a conspiracy. It's called idiocracy. Do you think idiocracy is a conspiracy? People being dumb and stupid and assholes, I have to come up with a conspiracy theory? I'm sorry, you're all idiots, okay? You're dupes, you're suckers. I mean, because Barnum said you can fool some of the people some of the time, and all of the people, you know, all the people some of the time, and all of the people, well, whatever. It's not his fault. You're suckers. I don't know why I would bother saying vibrations of what? Waves in what? You know, fuck. God damn it. I guess, you know, this is all ether shit again. That's really what we're going back to. I guess ether, ether. Well, yeah, ether is the real underlying problem, right? It's just people can't believe in nothing, so they have to believe something is vibrating. It's a jellyfish universe. You know, the energy comes from the jellyfish flapping. You know, the energy doesn't come from little force bits in the, you know, environment. Anyway, you know, it comes from the inside out rather than the outside in. It's that simple. It's a push universe versus a pull universe. They believe in pull concepts, where I think rational people say, what the fuck are you talking about? There's no fucking pulls anywhere. All right. Let's see, my message is not going through. Okay, well, too bad. Yeah, take the poo word out. Didn't Franklin Who sort of agree with you? Yeah, well, he pussied out. But he agreed with me for wrong reasons. So that's, you know, he got the right answer for the wrong reason. Because he did this stupid intuitive experiment. He did it all backwards and wrong. So he proved me right with a fucking flawed experiment, a fake experiment essentially. Then he did the experiment right and got the weirder result, and then just kind of walked away. So he's just useless. You can't communicate with him. He's an idiot savant or something. I mean, you just can't. You know, I've tried having conversation with him a couple of times even, and even that didn't work much. Yes, they're probably all sock accounts. Yes. I'm sure it's not Bill Gates because, you know, I hate Bill Gates. I frankly hate him less than I hate the Google turds. But, I mean, I hate him pretty deeply because he's just a crook. What a slime ball. I mean, to sit there and, you know, capitalize on the fact that computers ended up having operating systems, and he just ends up renting, you know, IBM, the operating system, and that just, but just the idea of what that represents to a programmer. If you were a programmer, Bill Gates was basically saying, I'm going to tax your product. No matter what program you write, I'm going to tax the fuck out of it. Nobody can use it until I let them use it. It's disgusting. I mean, nobody should have felt good about owning the copyright to the fucking operating system. I mean, he's just been bilking the human race. It's disgusting. It's like somebody owning the copyright on, you know, the round wheel. It's just grotesque to be paying this asshole for nothing. Something he didn't even write. He bought it from somebody else for $100,000 and then rented it to IBM for $10 billion. What a crook. So is hollow earth possible? Who are you talking to? What the fuck? What a pile of shit. Bill Gates' father was a lawyer and helped him write the contract. Yeah, I'm just saying the whole gimmick is so disgusting. The very idea of, oh, I snookered IBM. You know, it's almost like the Xerox and the mouse thing. You know, Xerox, you know, their research and development invented the mouse. And they basically gave it away, you know. They didn't sit there and say, oh, everybody who uses a mouse in the future has to pay Xerox. I mean, maybe that's why they went bankrupt, is because they, you know, they weren't as big a thieving, crooked, conniving asshole. I mean, basic technology, you just can't do that. You can't. It's like people who are selling cures for cancer, you know, to build their swimming pool. I mean, how can you build your swimming pool out of dying people? I mean, it's just a disgusting business to be in. Yes, I'm using the free alternative, but I'm just saying it's just, you know, it shouldn't exist as a problem. I shouldn't have to use the semi-round wheel. I should be able to use the round one. I mean, I should be able to use one that's made to work on my computer. All objects have the energy of 1/2 mv squared. Well, again, except spaceships. So an object with twice the velocity isn't as energetic as you might think. So I don't even know what that even means, but whatever. 1/2 mv squared. So again, you're making no sense, loser. I mean, 1/2 mv squared means if it has twice the velocity, it has 4 times the energy. I don't know what you're talking about. I don't have a problem saying it only has twice. You're saying you should think it has less energy. Isn't as energetic as you might think. I think it has twice the energy. Obviously, you think it has 4 times the energy. That's a big difference, moron. Yeah, I don't know what the fuck he thinks. He obviously doesn't reason very well. Your intuitive impression that it doesn't take 4 times the energy to go twice as fast is beautiful evidence of the fact that it does take 4 times the energy to go twice as fast. You can't prove it any better than the fact that you don't experience it ever. And what better proof is there than you never experienced it that way? I mean, you can't get better evidence than that. And of course, it not working in space, well, that's just icing on the cake. The fact that you can't move a spaceship with your kinetic energy, well, that just proves it even more, doesn't it? This is the school of Ian Gosling. I just want to understand that NASA doesn't use KE in their operations. Well, they used it don't. I mean, they use it for their jet engines and different things because all of that doesn't matter, right? They can make that number up any way they want to. They can say, here's a gallon of gasoline, and they can say it has 1,000 joules of energy, or it has 10 million joules. They can make up any number they want, and who cares? No one's going to check. So where it doesn't matter, they use it. Obviously, when it's life and death, then all of a sudden, yeah, let's go back to momentum because we'll survive. So when the the human hits the fan, they start using the real thing. And it's when it doesn't matter, when no one's checking, when it's not going to make any difference if I make up a fake number, then they say, okay, let's use kinetic energy. Because when they talk about like the thrust of their engines at takeoff, they'll say some number like 5 zillion gazillion megawatts of energy or something. They could just make up anything. It doesn't matter. No one's paying any attention. But if all you have is Coke bottles and whatever Energizer batteries in your spaceship to throw out to make your spaceship move so you don't crash, then it's going to be momentum. I mean, you saw the astronaut. He did the experiment right in front of you, right? The classic 10-ton train experiment. I mean, he banged a tennis ball into another tennis ball, conserved the momentum. He talked about conservation of momentum. Did he say anything about kinetic energy? No. Why? Because he would sound stupid. That's why. He didn't talk about the kinetic energy because it would look ridiculous. He's going to sit there and tell kids that, well, you see the energy this has? Half of that energy is now gone, and this object doesn't have it. Okay? It won't be able to do the same thing as in the universe. It lost the energy. It's gone. It's gone. Disappeared. I mean, just the idea that you could, like, deformation, that word sticks in my brain when the physics girl said, well, it obviously deformed and did all this stuff. And I'm saying, and you didn't use any momentum to deform it? So I can actually deform something. I can bend it and break it and crush it and snap it and do all kinds of things to it, and I don't have to use anything's momentum to do it. So I don't have to put in any momentum, but I can cause this to break in half. I could actually break it in half and not use any momentum. I mean, that is so ridiculously stupid. Why would, how could anybody think that's possible? That I could make a bunch of sounds, I could make sparks, I could make all kinds of shit happen, and I don't have to use any momentum. None. And that to me is another just decisive slam dunk. I'll never get a rational reply to that concept. That somehow you convert the energy into heat and other movements in other directions, and yet you didn't use any of your movement in a direction. You completely conserve your momentum, but you made a bunch of other stuff move. I don't even get the catalytic converter thing. I don't get it. It doesn't make any fucking sense. You can buy junk cars for almost nothing. I mean, you can't get more than like $150, $200, even if it's a pretty cool car, for the scrap metal. So if catalytic converters are worth $400, and it doesn't matter how old they are, it doesn't matter what they are, why the fuck can't I sell a junk car for $400? Because it's got a catalytic converter on it. And I could have a really good one, like a Cadillac. You know, I mean, I experienced this where I couldn't get rid of a car that really wasn't a piece of junk. And I couldn't get rid of it for a decent price. And you know, the seats were worth more than what I got. You know, the leather seats. I mean, the car was in parts worth a fortune, and because I had to move, I couldn't keep it. But anyway, and it just, it makes no sense that there's a market for stolen catalytic converters when you can buy junk cars for nothing. Take the catalytic converter off and then still sell it for scrap metal. The scrap metal value of the catalytic converter is almost nothing. I mean, if I remove that from the car, I haven't, you know, taken away the scrap metal value. So why the fuck wouldn't this be a huge moneymaker? There would be people making billions of dollars because they'd be buying used cars for nothing. Okay, they're getting the scrap value plus the $400 bonus of just ripping off the catalytic converter. And they're doing it without having to steal it. You know, do it on, you know, with some team of people that jack up the car and blah, blah, do all this crap to steal the catalytic. It just makes no sense. I mean, it's just proof of idiocracy that this could even be a thing. Stealing a catalytic converter. Who the fuck do you sell them to? Who the fuck is buying them? I mean, they can't catch the people buying the stolen catalytic converters? Yes, you okay. So why are you repeating what I've already stated, right? And you're going to do it with nothing. What do you mean by work in this context? It's just a ludicrous statement. Work is another word for doing useful energy. Okay, so you have to have usable energy to do work. All right, so work has some waste. That is, okay, you can do work and you need more energy than the work you'll accomplish. But I'm just saying work is elementally made out of energy. And so to do a job, you usually need 120% of the energy that you're actually going to do in work, okay? Because you're going to lose some to heat and all this other stuff. So work is just an analogy for energy. You have to have at least as much work energy, all right? You have to have as enough energy as at least the work energy value. And so that's all. But the words are synonymous. There's no difference. It's made of the same thing. Work is made out of energy. You have to have energy to do work. No other way to do work than to supply energy. There's nothing ambiguous in it. Fuck you in the ass till fucking dead. Do I even realize that? No, I don't realize it at all. I'm saying to you, it's a fucking piece of matter moving is fucking work. It's fucking energy. It's all the same fucking thing. And the simple fact is for us personally, we don't think it's work when we don't see it. Okay? But yes, there's more work to every bit of work you do. There's more to it than what you see. All right? When you walk down the street, there's more work than merely your mass moving from point A to point B. There's the work you do against gravity and the friction and all other kinds of things that were going on. Okay? But it has to be made out of energy. You can't do work without fucking energy. Obviously, the trains, if I took the work out of them, okay, I'm taking a percentage of their total energy. And at least I would have to put in whatever work I get out. I would have to have had put in at least that much energy in. So if I'm saying a 5-ton train going 10 miles an hour has a certain amount of energy, what I'm saying is that it's equal to the amount of work it can possibly do in perfect efficiency. All right, but it can't be, you can't get more work out. It's not possible than energy in. Work is how you measure energy. Is that too ambiguous? But you have to be a little bit scientific, you know. You have to know that sometimes it doesn't look like work. But there's plenty of energy. Ugh, just disgusting. Ambiguous. Thousands of videos. Thousands of drawings. Too ambiguous. Fuck you. I mean, I've detailed it all the way to the smallest scale, you know, and this asshole says too ambiguous. This is called work, the conversion of this little stuff going the speed of light into this big thing moving something less than the speed of light. That's work. But it's really just a transfer of momentum. And you can do it efficiently or you can do it inefficiently. That is, you can have the momentum transfer completely or you can have it transfer in some incomplete manner. And the problem is that all of this would be a non-subject if we could make the Newton's cradle where the velocities, okay, could be completely absorbed. That is, 30-mile-an-hour things, big things moving 30 miles an hour could make little things move at 90 miles an hour. But they can't. So we can't Newton's cradle. We can't conserve the energy in the direction it was moving. So we can't get all the energy into one object, into another object if they're different masses. But the lever can do it, okay? And that's that's why I've been saying for 2 years, asking somebody to draw a lever and show how it works. Because frankly, it does work, okay? I put the two mass over here, one distance. I put the one mass over here, and it balances perfectly because they weigh the same in the gravity. If I oscillate it, this will move at twice the velocity that this will move at. Perfectly consistent with momentum being perfectly accurate in describing the reality. Kinetic energy says there's twice as much energy over here as there is over here. A ludicrous proposition if you know anything about oscillators and how the only way they really work is they're exchanging the energy back and forth. The same energy back and forth. Fucking idiots. So, let's see what else there is and then get the hell out of here. Did you ever see a tightrope walker? Oh, we've done this already. Yeah, and they're doing it exactly for the reason that they can make a very tiny mass weigh a lot. Okay, so by putting the little mass way out there, they make it weigh a lot. So a very few atoms now weighs a lot because it has to move a huge velocity to cover the same distance. And so, yeah, it absorbs, it dampens all of the energy because you have a huge amount of mass, okay, far away from your body. And any movement of your body now has to move that tremendous amount of weight. Okay, small mass, huge weight because of the lever. Well, they do use exactly that. So you haven't seen that, but yeah, they've done that. Kind of the barbell thing. But the point is the lever works based on distance. So, obviously the longer you make it, the more it works. I mean, Bruce Uriney did some of those things, balancing different objects on his hand and, just pointing out the fact that that's the leverage thing. So the more mass you can get up there, the easier it is to control here because that can't move without absorbing a lot of energy. The point I'm getting at, fuck you, is that the small weight at a distance doesn't act the same as a proportionally lighter weight proportionally closer, even if its balance is. Yeah, I didn't say it does. Obviously, the multiplication is a lot smaller, so, but I'm saying it does work. The fact is, if you hold a barbell, you can see how it has a tremendous capacity to tip you over. You get it unbalanced and you're in trouble. Obviously, you don't want to increase your weight as you're on your feet as you're walking the tightrope. So obviously, you want a system that'll work where you have to use the least weight possible to create your balance. The least mass possible. So again, we have to be careful of these two words. More mass isn't going to help you. You want the weight to be further away from your body. Okay, that's the ideal. But certainly it helps to have more weight, more mass further away from your body. The further away you can spread out your mass, the more easily it is to maintain your balance. That's why just putting your arms out helps. I'm just saying that obviously I would argue that levers conserve momentum, and in doing so prove kinetic energy is crap, because a lever would be a free energy device. So if we could just prove that levers conserve momentum, then we can be done. That the fact is I can put the 10-ton train into one side of the lever, one distance from the fulcrum, at half the velocity, and I can produce this 5-ton train going 10 miles an hour on the other side of the lever. And if that's a fact, then this conversation should be over. All right, if you're saying everything conserves momentum, then okay, then isn't it over? I mean, I did the lever argument, but okay, I'll do it real quick. Oh, fuck. I mean, clearly you haven't watched any of my videos. Well, okay, clearly you haven't watched hundreds of the thousands of videos. Yeah. It is that bad, I guess, but, what can I say? It is a lot of videos. But, I mean, you could go to the debatephysics.com and you'll see most of the relevant ones are there. I mean, if we just establish that this is how a lever works, okay? I put the 10 ton, so I go here, 10 mass moving 5 velocity. And I plow it in here. And I put a 5 ton, I put so this is a 10 mass. All right, now I have a 5 mass here, 2 units of distance. Okay, 5 mass. Now if we say we conserve momentum, okay, this has to leave with 10 velocity. Right? Okay. So as long as we know that's my argument, that's how the physical universe works. There's no way around it. That's a law. There's no place for it to go, right? This fulcrum can't tell the difference. It thinks this weighs exactly the same as that, so it can't really tell any difference here. It can't absorb any of the energy, any more of the energy. So whatever the waste is to the fulcrum, that's a set amount of waste, and there won't be anything else. And so there's no argument here that I do this experiment one way, and I destroy 1/2 the energy, right? The energy I put in here will somehow produce something that has half the energy. How does it know it loses half how does the fulcrum absorb 1/2 the energy in this case? In this opposite case, again, I produce something that has 200 joules of energy, and this only has 100. So somehow I made 100 free joules. So it would be a free energy device. I could duplicate this over and over again and just keep making free energy. So it obviously is, it's proof that the theory can't be true. So if you believe in conservation of momentum, then you have to explain why when I do the experiment this way, I lose half the energy, and when I do the experiment that way, I gain twice as much, 2x the energy. So, you know, one way I lose, one way I gain, and it doesn't make any sense. But you know, you have to say that you don't conserve the momentum. The only way you can make it make sense is you have to say that this does not leave with a 10 velocity. It only leaves with a 5 velocity. I mean, it only leaves with a 7 velocity. Point. Well, in this case, 7. That's your argument. That's your 1.4 theory. All right, let's see. You have to consider the whole system or whatever. You have to consider the whole system. I'm just saying, who cares? Go ahead, consider the whole system and explain to me how the lever knows the difference. It knows when I put the energy in this side, it has to absorb, the earth gets pushed. But when I put the energy in this way, the earth actually gives us extra energy. The argument is what do you think the outcome will be? If you believe the outcome is this does move, okay, you know, this side does move with twice the velocity. The 5 mass goes twice, 10 velocity. If you concede that's the actual fact, then the argument's over, because again, I do it the opposite way, I make free energy. I mean, I do it that way, I make free energy. All right, what holds the fulcrum in place? It's on the most solid thing we can find. It's, whatever, on top of a big giant 500-pound rock. In conventional physics, work equals the product of the force, strength, and the distance traveled. Whatever. Again, I can't say this distance thing means absolutely nothing in the real world, okay? It's proven to mean nothing. In space, something going twice as fast only goes twice as far. You do know that, right? Their description of work is straightforward. Your is not. Well, you're a liar. Fuck you. Let's see. So this is the Bruce guy. It's just silly. I'm sorry. You can tell me what their theory is, and I'm saying they have no evidence for your theory, okay? Theirs and your theory are completely unevidenced piles of shit. You're going to impact a lot of momentum into the fulcrum. Says you. So you say that levers lose a lot of energy. I'm arguing, no, they don't. That it's minimal. Like springs, like they're probably more efficient than springs, actually. So I disagree entirely. You're going to be pushing it down, right? I think I described the circumstance plain enough. I'm just saying, look, when Brozo did the experiment, okay, he had a spring on one side, so it's a constant force. He moved the lever a constant amount, and yes, half the mass at twice the distance on the lever, left with twice the velocity of a full mass, 1 unit of distance. I'm just saying that that's what I say happens. You either agree with it or you don't agree with it. You either agree that I could use a lever to convert a 10 mass 5 velocity object into a 5 mass 10 velocity object. You're either going to agree or disagree what will happen. What do you say will happen when I put the 10 mass going 5 into one side 1 unit of distance, and I allow the half mass twice the distance going twice the velocity to go out the other side? Will that or will not happen? I'm saying of course it'll happen. Now, we don't have the experiment, right? It seems so elemental, like somebody should have done this experiment somewhere. What's so difficult, right? I mean, just drop a 10-pound weight on a seesaw, okay? And put a 5-pound weight twice the distance on the other side and see how fast it moves. What's so complicated? I would say, of course, it can't, because that would be free energy. So, okay, so I'm just saying, you're saying that levers don't conserve momentum. But I've not done the experiment either. Okay. I'm just saying there's no logic saying the fulcrum is absorbing the energy when I push on one side and the fulcrum doesn't absorb the energy when I push on the other side. I think that's silly. But they also believe. I mean, what do you think is going to happen? Do you think you could feel the difference? So if I put a 10 mass, I'll draw it. What the hell? It's not that much work to draw it. And they've argued that no, it doesn't work that way. Blah, 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 blah. Right? So, I mean, this is. I'm saying, I gave this. This would be a thing. I'd love to do it in an amusement park, right? Because if it isn't true, then they should be doing it. Because it'd be kind of amusing to see. So if I blinded you and you can't see what's on the other side, I'm arguing that if I hit this, if I push on the same place here, okay, this is where I'm going to push, right here. All right, now I put a 10 mass here. Okay, all right, I put a 5 mass here, twice the distance. Or I put a 2.5 mass here. Okay, yeah, you can still see that. Okay, 4 units of distance. It should be 4. 1, 2, 3, 4. Okay. And I would argue that you won't be able to tell the difference pushing on this side of the lever. So when you push on this side, you're going to feel the same force, the same work, the same motion. Because no matter where this, so if the 5 mass is here, you have to understand that this is going to move and this is going to move. If the 5 mass was here, this part of the lever is going to move exactly the same. And if the 2.5 mass is way out here, this part of the lever is going to move exactly the same. This same amount of motion here. Whether this is here or this is here, this piece of the lever will move exactly the same. And this piece of the lever will move exactly, it doesn't matter which one of these I do. So theoretically, I'm arguing that there's no way to tell. You can't tell the difference between which one I put. If I put the 2.5 out there, put the 5 here, or I put the 10 here, you cannot tell the difference because it's the same weight. It's a proven fact. I put the same weight here. All of these things will balance that weight. It'll all be exactly the same weight. This will balance perfectly. It'll say it's the same weight. So, but they say they can tell the difference. So they argue that they can tell the difference. So if I had the 5 mass, there would be more inertia. The magical inertia would show up. Inertia. The magical inertia would show up. And somehow I wouldn't be able to tell I would be able to tell the difference. So even though they weigh exactly the same, even though the weight on this side of the scale is exactly the same, I'd be able to tell the difference. Don't you think that's a ludicrous proposition on their part? But again, no experimental evidence. It conserves momentum, but you need to take into account the momentum that goes... Again, I already took it into account. I'm saying, okay, how can the scale tell the difference? The scale only knows the weight, not the mass. It only knows the weight. The force to balance it is the same, but the acceleration you would get is different. Well, so what? To the different moment of inertia. So more bullshit about a moment of inertia. Just more absolute nonsense. So it's just gibberish. Sorry. There's no moment of inertia. There's no such thing. A moment of mass. I mean, it's just silly talk. Okay? It's a simple enough proposition. Do you think you can tell the difference? You're going to press on this part of the lever. Do you think you can tell which one of those objects I have on the other side of the lever? Just answer that question. The acceleration would be proportional to the weight. I'm just saying, that's all you're detecting is the weight. That's all there is. That's all that anything produces is weight. Everything produces weight. When it hits something, when two things hit something, there's a weight between them. It's a weight contact. All contact is weight contact. Okay, so Bruce says I can tell the difference. Okay, so that's the argument. I'm saying no, you couldn't. So I'd love to see the experiment because there's no way you can tell the difference. I'm surprised you think so and then argue for conservation of momentum. How can you tell if they have the same momentum? How could you tell? It doesn't matter. This side of the lever moves exactly the same. You're still not getting it. If I oscillate it with any energy I put in, and I oscillate it with this out here or this here or this here, this moves exactly the same in all three circumstances. This moves exactly the same. How could I tell the difference if it's showing me that there isn't any difference? That the deceleration and acceleration rates are identical right here. This piece of the lever moves identically no matter which one of these objects I push. And I place on the lever and I push it. This piece of the lever has to move exactly the same, or they wouldn't balance. This isn't about angular momentum. There's very few angles we're talking about here. Let's use pistons that go up and down only, whatever. The angular momentum is irrelevant in the tiny amount of movement we're talking about. It's for all intensive purposes up and down motion. It is not rotation. All right. Well, anyway, so all this. So the question came up: why am I the only one? And what does that mean? It means, like I said, there's no other choice. You're belligerently stupid, and you're just demonstrating it. You have no evidence you can show me, no physical experimental evidence, and yet you just keep insisting that you can have this duality of two kinds of energy, that makes sense somehow, okay, and that everything Newton, Galileo, and Descartes discovered and understood was perfectly explained by momentum, and yet you think there's some necessity, something vital or important about understanding whatever this 1/2 mv squared crap is that doesn't have any experimental evidence supporting it. So there's no evidence supporting it. There's no evidence Newton got wrong answers with MV. There's no evidence MV is broken. Yet and there's no evidence that 1/2 mv squared fixes it, and yet you're just going to belligerently defend. Okay, got it. You're talking about rotating masses. I'm not talking about that at all, so fuck you. I just pointed it out. It's a circle, for fuck's sake. You're using this little tiny bit of the circle that's going straight up and down. You're not using this part that's going sideways at all. So fuck you. This isn't about angular momentum, you lying sack of dirty, smelly shit. I mean, it's just such fucking nonsense. The angular momentum is a tiny portion of the momentum. It's a tiny portion. It doesn't mean anything. Can't possibly have an effect on the experiment. And all of the pieces are being affected by it to some extent or another. So fuck you. Too silly. I mean, all these evasions. Evasion. But I've got you on the record. You think you can tell the difference. Even though they weigh exactly the same, you can tell the difference. Okay, I got that. I'd love to test you. And you can show me how 10 pounds doesn't weigh 10 pounds, doesn't weigh 10 pounds. How you can tell the difference between the 10-pound thing and the 10-pound thing and the 10-pound thing. And the irony is the lighter things are heavier. Yeah, that's the funny part. You can tell because that lighter thing is a lot easier to move. Oh no, I guess it has to be harder because you can only go 1.4 the velocity. So yeah, it doesn't push. You can't make it happen. Even though it oscillates perfectly, it won't happen. Alright, I guess we'll call it a day. Somebody can say something profound very quickly. Which isn't likely. So, yeah, there's just nothing to say. You've had 350 years, millions of scientists, billions of dollars, and you haven't proven any of this crap. Let's see. I remember a video where one of your detractors had two levels oscillating. One with a 5 weight and a 10, and the other with a 10 and a 5, and they went very differently. Yeah, and I explained why those experiments were fundamentally flawed, because the levers weren't the right length. They had springs attached to them. It's a catapult is different than a lever. Okay, so you got a fixed bearing and you put a mass on something, and you're moving the whole lever without a counterbalance. So there's nothing balancing the piece of lever here. There's no other side balancing it. So its weight is always got to be pulled by the spring. The spring has to pull the weight of the actual lever. All right, so obviously you're not going to get the same results, because the fact is you're dissecting, you're spreading the weight over a much larger system. You haven't eliminated the lever by creating a counterbalance to the lever. So if you counterbalance the catapult, then you could make the argument that they should move at the same speed, but they won't move at the same speed if there's no counterbalance. But anyway, I argued all this stuff already. So you want to drag up this crap, that's your business. Their experiments absolutely suck. Every single one of them is flawed. They haven't done anything straight up and fair ever. Okay. Anyway, that spring is doing what I would be doing. The spring can't tell the difference, just like I could. The spring can tell the difference. So again, you're arguing it continually, and I've already debunked it. It's not a lever. If you don't have the same weight on both sides of the fulcrum, it's not a fucking goddamn balance, you idiot. It's an imbalanced balance. So you weigh differently if the balance is imbalanced. Yes, if I start with an imbalanced balance, then I can't do a balancing two masses on the balance anymore if the balance is imbalanced. Retard. Oh, fuck. Well, thank you for just making yourself that much shittier. Yeah. Bring up already debunked crap shit experiments. So we know what camp you're in anyway. But you've already proven it. You've already demonstrated. You're not just accidentally stupid. You're not stupid for good reasons. You're stupid belligerently. Again, you have no physical fucking evidence except these shenanigan experiments done by fucking Alzheimer's, whatever, Asperger's, people who can't figure out how to not, blow snot on other people because they have Asperger's. I'm in the everyone who isn't your camp. Well, that's fine. Fuck you. It's about making arguments, and your arguments suck, and you just showed how they suck. Because you had to desperately reach for a piece of shit. A shitty experiment done without any thought or reasoning or logic, and you think it's great science. It just demonstrates why you're an idiot. You're an idiot because you wish to be one. You identify with fucking cheaters and liars and fucking slandering pieces of scum. So go ahead and out yourself as a scum sucker. Yes, that's the camp I'm also in. If you're going to make your assertions, then make them with something called a fucking piece of decent, not dirt, as evidence. Something not covered with shit. I mean, Brozo doesn't even own a ruler that you can actually read. Let's see the fucking contest between the 5-ton train going 10 miles an hour and the 10-ton train going 5 miles an hour. Let's see the fucking goddamn tug of war where the flag should obviously go racing in the advantage of the 5-ton train because it has twice as much energy. But we will not see the evidence because it can't be manufactured. That's the truth. Only liars and shysters and creeps can manufacture it. Well, I showed Professor Lewin manufacturing it, frankly. You know, he did a free momentum experiment. You know, he actually did make free momentum. But we know he didn't actually do that. Because what he actually did was just cheat. Cheating for the theory. You know, that's all they have. They don't have good evidence to prove the theory. All they have is lies and distortions and perversions. Alright, so I guess we're done now. Okay, so let's see how many slobs are here and get out of here. 11. Pretty poor, but consistently poor. So that's what we're stuck with. Anyway, so till the next time and such, and pretty much fuck you. Yeah. God, the idiocracy. Oh, another little comment popped on. I guess I should see what it says. Yeah, let's see. You turned 100 momentum into 133 in one direction and 33 in the opposite direction. Yes, just completely silly. No, it's conservation because the unmomentum went that way. You know, unmomentum. It's kind of like anti-momentum, but it's unmomentum because it uns your other momentums. You know, so you can yell that way, and then you yell this way, and it undoes your yell that way. Yeah, it's really cool on momentum. Yes, they do it anyway. Plus, minus. Yeah. I did minus heat, so 135 watts. Okay, minus the 33 watts. I put that way. I ejected minus heat. The minus heat will undo the plus heat. Yeah, okay. It's just too ridiculous. On its face, it's ridiculous, and you people believe it. I mean, it's just, and I'm supposed to say, what? God damn, I live on a planet of idiot zombies. Heat is energy is scalar. By definition, because we called it that. It's like the Holy Ghost. You know, his name is really John, but we call him the Holy Ghost. Momentum is a vector quantity. Says you. Just baby talk. It's absolute baby talk. Heat can be in one direction. Trains are in one direction. It's just baby talk. Oh, we're going to call this energy a scalar, a magical scalar energy, even though it's a train on tracks rolling, right? We're not talking about its nuclear energy, right? It's, you know, its nuclear energy is in any direction, but no, obviously its momentum-related, MV-related energy is clearly dictated by momentum. The MV is right in your equation, and all of a sudden you take the vector of MV and somehow you scalarize it. For what purpose? To contrive nonsense, to contrive some notion that you can make free momentum, and it's not really momentum because something else went the other way and it undoes it, which doesn't happen again in space. Can't, you can play this silly game, but it's just a silly game. It's all real energy. It happens in the real world. Okay, all I do is separate the time when you do these events, and all of a sudden these events aren't subtractable anymore. I mean, it's just, again, just absolute nonsense. Absolutely. So, just all jargon, all crap. You'll never show where, hey, we discovered it's a vector quantity. Go show me when they discovered it's a vector. The magical vector discovery. Yeah, we had some kinetic energy in a jar over here, and we said, oh yeah, that's scalar. And then we had some momentum over here in a jar, and we said, oh, that's a vector. Yeah, show me that experiment. It's just such a pile of shit. Oh, God, it's just such shit. What's going that way undoes what's going that way. Sure it does. All right. I should have left before they showed themselves to be even dumber. Ugh. Fucking people. Velocity is a vector. He says it again. Mass is a scalar. What does that even mean? The mass part is a scalar? So if I say mass is a scalar and velocity is a vector, so if I multiply m times v, it's a vector, and if I do v times m, it's a scalar? I mean, fuck you. Too silly. Just too fucking silly. Yeah, you can keep saying it. That means it has no direction. So the 10-ton train, the 5-ton train going 10 miles an hour is on a track going in a direction, and you're going to tell me, well, the kinetic energy isn't in that direction. Amazing bullshit. Just absolute fucking bullshit. I mean, there's no arguing with people this fucking insane. It's a different kind of energy. It's in any direction. Even though the train is on a track going in one fucking straight line direction, I'm going to pretend it's some sort of magical energy in no direction. Oh, it's so dishonest. It's just so disgusting that people resort to this mush. The motion of the train has a direction. Yes, and the scalar value of its kinetic energy is a measure of its motion in that direction. It's not a measure of its fucking absolute energy. It's a measure of its motion in one direction relative to coordinates. The mass is just a number. What the fuck? That is such baby talk. The fucking velocity is just a number too, fuckhead. Oh, amazing bullshit. Just amazing bullshit. I just can't believe they wallow in that. It just proves they're just bandwagon riders. Because they don't even ask the question. Well, where did they come up with this crap? I mean, how did they see the kinetic energy was not in the direction the train's moving? I mean, where did they see that in the experiment? It doesn't matter. It has a direction. Of course it has a direction. All motion has a direction. Duh. I mean, those are Newton's laws. So what? The only way your kinetic energy has any meaning is because the mass has a direction. The same exact fucking vector is involved. You can't undo the vector of the direction or the velocity by just saying so. I'm going to make a magical substance that's in any direction when it's clearly not in this very specific direction. It's like saying a laser beam isn't going where the laser beam is going. It's like going everywhere. The light's going everywhere. No, it isn't. It's just it's a lie. It's just a preposterous pile of nonsense. So, well, anyway, there's no point. There's no arguing with people this stupid. I mean, this fucking dishonest. To sit there and say you understand why kinetic energy is a scalar. You understand why it is. You understand exactly how the motion isn't in the train isn't driving down the track, and the energy isn't in the fact that there's a mass moving in a very specific direction and it's going to hit a very specific thing. You understand completely how that's not real. I mean, fuck you, do. Oh, God, Jesus.